Most of you made it back after the carnival last night. Anybody win prizes at any of the games? Very few people won prizes. That's we'll have to make it easier next year. But that was a fun event. And now today we've got another big agenda for you. So let's kick it off. Another reminder that we're live streaming and recording if you forgot from yesterday. Just remember that you may show up on video somehow. Need to get that out of the way. Wanted to give a little background on our logo as well. Our logos actually have some thought put into them. So we wanted to get an explanation from the designers. I thought it might be interesting to showcase how the logo came about each year. And this year, they actually put a lot of thought into the colors to represent the Google colors and show what everything that Google stands for. There's also a emphasis on the site we hold it. So they wanted to incorporate a little background about Sunnyvale and what the location it is. So I wonder what next year's logo is going to look like. We'll see. All right, a little stats on registration. We had over 1,400 attendee applications, out of which we chose a little over 250 of those to actually attend in person. So you all are among that group that we narrowed down. We have, and actually as scientific process as we can get out of this, there's some random selection and weighting based on getting a diverse crowd representing different geographic areas, backgrounds, history in the industry. We get a number of factors that we plug into it to try and get a great overview of the industry. So everyone here can share ideas, take it back to the companies you're from, and showcase those ideas. But for the people who couldn't come, we of course have the live stream. We present all this information out there in the world for free. So hello to everybody on the live stream. Thanks for watching. This is great. Now that I'm on YouTube, I finally have done something my daughter can be proud of. She knows what that means. And 208 speaker proposals, which we also had to narrow down by a similar process to get just the great overview that we've had so far and that we'll have today of different types of challenges that are going on in the industry and things that everybody is dealing with. So I'm glad we could talk about that. And another great thing we were able to do this year is to provide diversity scholarships for people who may not have been able to come otherwise. We put up a notice for applications for that. Google put up the funding for that to be able to include those people as well. We had an overwhelming response to that, 273 scholarship submissions. We originally had budgeted for 6 scholarships, but just out of the overwhelming number of applications we got, we asked Google for more money. They're used to people asking for more money, and we were able to get that and double the number we were able to provide this year, so that's been great. Okay, a reminder about lunch. I think yesterday went pretty well, but everybody kind of has the system down. You know what lunch is all about. So here's a reminder of the cafes again over here. We have Cornerstone with their local menu. We have Fresh Market, which has the big salad bar and sandwiches in TC1, and then TC4 is the big area with all the variety of options. So what we're going to do for lunch today, here's the other options for TC4. What we're going to do today is we'll have 3 organizing members outside here at lunchtime. They're going to have signs they'll be holding up similar to what Ari is holding up in the back there. So it'll look, don't worry, he won't club anybody with that. It's only for illustrative purposes. But we'll have signs up with each cafe. If you're interested in a specific cafe, find the person with that sign, and they will be leading the group to that building and letting you in for lunch. Another reminder about the question page on the live stream. If you have questions, please submit using Slido app that we have. Use the event ID GTAC 2016 to ask your questions. We are trying to achieve a balance between staying on schedule plus getting enough questions answered after each talk, and making sure everybody gets questions answered and staying on track. It's a tricky balance, trying to manage that in real time. But that's what we're trying to achieve, so don't feel badly if your question doesn't get answered. The benefit of being at the conference is then you can go up to that speaker specifically and say, hey, I was wondering about such and such, my question didn't get answered, I'd like to talk about it. One feedback we have gotten though is that we don't have a way for questions that didn't get answered to be archived and answered later, which is one thing we'll need to look into for next year. And I think that is all I had. Trying to stay on schedule myself. And the other things I wanted to announce, we will have the real-time translation going on over here. If there's anybody who has a need for it and didn't know that we were providing it on the screen over here, go ahead and make a seat. If anybody does need this service and you're sitting in a seat they might need in order to be in front of the screen, please give up your seat for that. And all speakers, don't forget to check in with the audio team in the back before your talk, during the break, or if you know your talk is upcoming, go get mic'd up for your talk so that you're ready to go on time. And today we'll try to keep it on time. And I think I'm doing well. I think I'm ahead of time. So since I'm ahead of time, I did not get any more emails from my mom, but that's okay, because we now have Google Assistant. So I can just, and Google is not making technology to replace moms. That's not, it's not the intention, but we do have the Assistant you might have heard of. So I can, hey Assistant, how am I doing today? It says I have no friends, but that's actually correct. That's a correct answer. That's a valid response, so it's working. With that, I will head into our first keynote speaker, second keynote speaker for the conference, first one today. We have Niranjan is going to talk about the developer experience at Google, and I'll hand it over to him. Interesting fact, Niranjan actually interviewed me when I was applying at Google. So don't let that bad decision factor into your evaluation of his keynote. But take it away.
Thank you. All right, how's everybody doing? You all had enough caffeine to last through the day? All right, just making sure. Please give a round of applause to all the organizers. I think they've done a fantastic job with all the logistics and facilities. So, my name is Niranjan. I work at Google on developer products. Particularly, I work on something many of you might have heard of. It's called Firebase. We launched it as a mobile developer platform a few months ago at Google I/O. I specifically focus on a lot of tools and infrastructure that are geared towards app quality And the thesis of my talk here, my keynote here today, is how we've actually demonstrated that by investing in developer experience, you can have a positive impact on app quality and quality of your software and code base in general. I'm going to speak mostly about mobile, but a lot of the things and the lessons that we've learned are fairly generic, and you could potentially apply them to other areas as well. I think towards the end of last keynote yesterday by Mansi, you probably saw some of the challenges with the wide variety of Android devices and the large diversity in devices that's actually making it challenging to be a mobile app developer. People out here who've actually built and tested mobile apps can feel that pain pretty well. So it's cases like these where investing in developer experience really matters, and hopefully I can convince you of that as we proceed. But that's me and that's my name. So first of all, let's just take a moment to recap how we got here. Software development in general is being democratized. There are far more people writing software today than there were just 5 years ago. Just take a look around yourself, just take a look around this room, right? Like there's people from all walks of life, from many countries. We had a great diversity scholarship program which allowed a lot of participants to fly out here, which was awesome. And that trend is actually apparent as you sort of look at apps and as you look at people who are building software across the world. And it's gotten that way for multiple reasons. Number one, there has been a phenomenal shift and growth in computing. If you actually look at the previous generation's dominant computing platform, PCs, it took them about 2 decades to get to 500 million users. It took mobile phones less than 4 years or 5 years to get to 1 billion devices. And that growth continues today. Like by now, there's about 3 to 4 times as many mobile phones as there are PCs. This probably is not news to most of the people out here. Most of you have actually seen this graph before in some shape or form. But the reason why I'm actually here talking about this graph is because there's just a profound shift that's happening in terms of the growth of mobile apps, and it's not showing any signs of slowing down. You can go to countries today where you can buy a pretty good mobile phone for less than $100. And it actually is a pretty good device. You can get most of your things done on that. And that has been the only computing experience that almost 1 billion people have had. Like there are people who've never ever used PCs, don't have email addresses, but the only thing that they've had is a mobile phone. And that's actually a big factor in why there are more app developers, because there's actually more people using computing devices. Not just that, but we as an industry have also done a pretty good job of lowering the bar for what it takes to become a software developer. So if you consider a few things, number one, education. Back when I was studying computer science, you pretty much had to have a 4-year degree or an equivalent to have a meaningful career in computers. And most of the interesting course material was actually taught only in colleges and universities. You could get some technical education here and there, but it wasn't really well fleshed out. If you look at things today, things like Udacity, things like Coursera, the open courseware that you have available from MIT, there's a bunch of things available from Stanford. You can get most of the great content available to you for free or at very low cost. Just for us in Google, we've actually partnered with a bunch of training institutes in India to have a lot of developers go through a Android Nano degree in partnership with Udacity and a few other companies in India. And we've seen a lot of great success. And it's what this means is like more and more developers are actually coming out and building great apps, and they're being trained to be mobile app developers. Not just that, but the tools of trade are now free or really cheap. How many of you have worked with Visual Studio before in their past? All right, quite a few, right? You probably remember you had to pay hundreds of dollars to actually get a license for Visual Studio, probably cheaper if you're a student or something. And if you actually had to deploy your apps, deploy any services, you had to probably build your own services and data centers. And if you needed any other custom software, you actually had to pay more for it. Now, if you look at things like Xcode or Android Studio, they're basically free, or they cost less than $20 or something like that. And that's actually profoundly important because it actually enables more people to tinker around with software, and they don't need to invest a lot of money in just like trying to prototype their ideas, and that's awesome. Not just that, but there's a lot of great frameworks and building blocks that apps use to build great experiences, and those are basically available for free right now. You can go all the way from cloud services, where Amazon Web Services and Google Cloud and Microsoft Azure and all these other things. You can basically launch a free service today, and as long as your traffic doesn't exceed a certain amount of volume. So you get like world-class data center and server support for free. You can build almost half of your app for free. There's like amazing app development frameworks like React Native or Firebase or Fabric by Twitter and a few more. And you get a lot of the things that you would have needed to do to build an app basically built out for free. And that's spurring more and more app development as we go forward. In general, I think with mobile, open source has also truly come into its own and has really hit a good level of maturity. If you look at GitHub today, it's a very, very vibrant ecosystem. People are forking repositories all the time. People are sharing things at a far greater pace than they were sharing before. And that's actually led to more innovations in software and more people creating good experiences. Just to quote an example, Google released a machine learning library called TensorFlow about a year ago on GitHub. And in just a year, it's been forked more than any other library out there. And this is something which is like cutting edge neural networks, machine learning, image processing, those kind of things. And it's now being used pretty widely all over the world. So naturally, as you have better tools and free or cheap infrastructure and open source and great education and things like that, you see that the number of apps is actually going quite high up. There are way more apps being created today than there were a few years ago. It's important to note that the iPhone was launched about 8 to 9 years ago, and less than 7 years ago, there was no apps, there was no such thing as mobile apps. From that point until today, we have close to a few million mobile apps. So just think about the explosion that has happened, right, in terms of how many apps are out there. So things so far seem great, right? Why am I here talking about problems? And we'll get to that in a bit. Not just that, there are now multiple companies who've built successful businesses, and they started only as mobile apps. Like the companies that you see behind me, all of them actually began as mobile apps, and they're probably still just mobile apps. Like I don't think you've used any of them as anything other than a mobile app for the most part. If you just take the valuations of these companies, I think most of them are still private. If you just take the valuations of these companies and you add them up, they would be in the top 50 in terms of GDP by revenue of countries, right? Like, so think about just how big and phenomenal this thing has been from a revenue growth perspective. When you have that much money flowing through your apps and through your services, quality certainly starts becoming really important because any loss in revenue is any loss in usability or stability means a drop in revenue, and which means people get very, very unhappy really quickly. So as these industries have matured, you now start to see people paying more attention to quality and testing and all those kind of things on mobile app software. So we did an analysis earlier this year. We took a bunch of reviews and data and crashes that were being sent to the Google Play Store. We did a bit of sentiment analysis by actually parsing the review text. And we also looked at some historical trends and data for crashes, as well as why people rate things a certain way. So the pie chart that you see behind me is actually the 1-star, is the reasons for why people give 1-star rating to apps on the Play Store. And the overwhelming reason for why people get such low ratings for their apps is actually stability issues. Somebody saw a crash. Like you tried to use an app, it crashed, you got angry, you left a 1-star review, and you tried to express your frustration that way. For people here who are actually working in software engineering and who are practitioners of software engineering and testing and such, the answer is pretty obvious to you, right? Like the reason why somebody crashed was because they actually didn't test properly. But and most of the app developers also kind of probably know it, but yet you have so many apps out there which actually have this like proliferation of crashes and stability issues and such like that. Even if you look at mobile apps in general, in the Apple App Store or the Android Play Store, you see like this a small number of really great apps, but then there's this long tail of apps that basically get downloaded maybe 10, 15, 20 times and nobody else uses them afterwards, right? Like, so it's a clear sign that the quality tapers off really quickly, and we aren't really doing a good job of helping bring up the level of that quality. One of the reasons why it's so hard, and I think you probably saw one of the charts in Manasi's keynote yesterday, is there's this compounded complexity when it comes to mobile app software. Just thinking about mobile apps, you actually have about 2,000 to 3,000 different device manufacturers and different hardware units and hardware form factors and such. If you kind of take the summation of all the versions of iOS, Android, and a few other operating systems, you get about 100 different OS variants you need to test on at any given point of time. There are anywhere between 700 to 800 global carriers that people actually connect to the internet on. Not to mention different cloud providers, different network topologies, and things like that. So if you actually want to really do a good job of testing across all of these, like you're looking at a insanely high number of permutations and combinations that you actually have to work with. And as a result, it actually becomes a big daunting challenge for you to build a really high quality app, especially if you're like a 2 or 3 person startup and you're just getting off the ground and you now have to like think about this entire giant complex matrix. It's probably easy for companies like Google, where we have a lot of engineers invested in solving these problems, or other companies like Facebook, or even like banks and other things. But imagine if you're just an up and coming company, you're a few students in India or Indonesia or somewhere, and you have a great idea and you're trying to get it out, and now suddenly you have to deal with this giant set of permutations and combinations that you have to deal with. So what we found is if the reason why actually people get into these problems is because while we've done a really good job of making it easy for people to write great apps, we are not quite there yet as an industry when it comes to helping people test apps better. And I think if you look at the user experience of our testing tools, if you look at a developer experience of how what it takes to write apps and build well-tested software, there's a lot of rough edges, and we're actually we need to do a better job of addressing that collectively as a group. So I'm going to try and talk about a few examples of what we've done at Google to sort of address these things. The things that I'm going to talk about are actually products that you can go and use today. And we have more announcements to come in the upcoming months as well. So this is by no means a complete list. There is a huge universe similar to the one that I'm going to talk about that gets used internally at Google as well, and it's a continuously evolving space. There's also a lot of great innovations and solutions that happen outside Google in other companies as well, and I'm going to try and talk about things that I'm more familiar with myself, that I personally work on, in a hope that we can actually inspire you and help you. So going back to this whole permutations and combinations of devices and complexity with all the hardware fragmentation as well as all the topology and other things. So we realized that we want to help all of our app developers make a living. We want to help them build better software. We want their apps to not crash. And we realized how hard it is. Like, we actually did a lot of user studies, and we even have our own examples internally where people just want to test their app on a bunch of devices, and they don't really care about like buying devices and setting them up and maintaining them. Nobody has the time to do that. Like, especially if you're a small team, like it takes a lot of your time just to do that. What people want is a simple, easy to use cloud service. If you're not really doing maintenance of your own data centers and your own services and backends and things like that, then you probably should need to do it for your mobile apps as well. So earlier this year, we announced something called as a Firebase Test Lab. And we've been working on it for a few years. We also acquired a company called App Purify along the way, and they joined forces with us. And so we've launched this service, which there's about a few thousand devices in our data centers, and you as an app developer can actually rent them, and you can run your tests on them. We've paid a lot of attention to user experience here, and we try really hard to meet you, the app developer, wherever you are. If you use Android Studio to build your Android apps, we actually have the functionality and plugins baked into Android Studio, so you can actually, while you're writing your tests, you can actually just run them on our lab and get results back right away. We have a good command line library where you can actually use it for your own local runs and local debugging, where it'll automatically take your tests, ship it to our lab, run them, bring back results to you. We also have plugins that work with all the popular continuous integration systems like Jenkins and Travis, so that companies who want to set up their own continuous integration can do that. And we actually do have paying customers like American Express and others who are actually doing that. There's supposed to be an animation there, but anyway, imagine that there's an animation of a robot. I think the slide got kind of messed up. What we realized quickly was there's still a gap in maturity when it comes to testing. Most of the, simply providing a lab is not enough, because that assumes that app developers have actually done their job of writing tests, and they've actually done a job of thinking about testing to begin with. But most companies and apps are actually just starting up, and they don't really have the ability to, or they don't really have the time really to actually go in and do testing ahead of time. So people want something quickly, and people want to get a quick view of quality of their app. So what we did was we actually took the concept of monkey runners, which is like a random key press on your app, and we turned it into a more predictable sort of crawling mechanism. So we built this robot which actually crawls your app automatically, and it goes through all the UIs in your app. It has a bunch of intelligence baked in, and it can do things like it knows when it's seeing a OK or cancel button, or it knows things like you're about to encounter a login screen, so it can kind of try to bypass that. But the goal is we want to try and exercise as much of our app as possible in the hopes of getting it to crash. So most of the device-specific bugs that happen are actually crashes anyway. So we try to sort of give you that data as quickly as possible without requiring much effort from you. So it's a very simple one-click thing for app developers. You go to firebase.google.com, you upload an APK, and in a few minutes you get a good analysis done over a wide variety of devices that will tell you where your app has been crashing or performing badly or things like that. We quickly realized that once app developers actually start writing tests, start using a robot, and they start finding crashes, they're like, that's great. I know my app crashes now, and I would like to prevent it going forward. I want to do a better job of not having my app crash going forward. So they want to write tests, but it's kind of a daunting thing, and they don't quite know how to get started. There's already great documentation out there, like Stack Overflow is really helpful. The Espresso community is pretty vibrant, and so are other communities as well. But still, if you just want something quickly done, you just don't have the time to invest a few hours or a few days sort of setting things up and studying things, etc. So what we did was we partnered really closely with the Android Studio team, and we launched something called as the Espresso Test Recorder. It's actually available today in Android Studio, so if you download the Android Studio, you can actually try it today on your phone, on your laptop. The way it works is you simply take your Android phone, you hook it up to Android Studio, and you do a bunch of actions, and we'll generate Espresso test code for you. That's it. You don't have to set up frameworks. It's all baked in. And these are actually working functional tests. And since it's just Espresso test code, you can actually do your own assertions. You can change things. You can add more assertions. You can modify tests. You can copy that test and write 10 different tests. It's all up to you. You're just given with working test code. And this has actually been a big hit with app developers. We've had a lot of tests and great feedback already, and it only kind of became generally available a month or so ago. So the uptake has been pretty exciting. So we've had about 1 million plus tests already written and run on the Firebase test lab, which I'm really happy about. This is a quote from Jet.com, one of our large partners. We actually had them present with us at one of our conferences in Berlin last week, and they basically got rid of their own lab, and they're just now using Firebase test lab. And I think that's it's good to see positive feedback from our customers and getting good validation for the work that we've been doing here. So what we realized that was it's great. Like we actually got people to care a bit more about testing. We've given them tools. We've tried to be in their workflows. We've tried to help them sort of along a path. Like we've tried to build a well-lit, guided path for them to do testing for their apps. But it's still not enough. Like people still don't really discover Firebase as much. Like they don't really think of it when they want to sort of think about testing. It's still not in people's workflow as much. So one of the things that we've been trying to do is actually really help app developers get ahead of this testing curve as much as possible. So we also worked really closely with the Google Play team. So one of the things that every app developer does is they actually want to, once they write their app and once they think it's good enough, they want to publish their app, because that's the only way they're going to get their friends and family to play with it first, and hopefully the word of mouth will get out and their app will become popular and they'll be billionaires in a few years. But you first need to publish your app. And since we have a very sort of centralized mechanism for doing that, we actually work with the Play Store team where while you're publishing your app, you can just check a box saying that I would like a free robot run. No action required, nothing extra that you need to do. And we actually give you that for free. And what we do is we give you something called as a pre-launch report, where you as an app developer, even if you don't know anything about testing, you can still publish your app, and and when you publish your app to the alpha or beta channel, in a few hours, you'll actually get a pretty detailed report. Actually, in a few minutes, you'll get a pretty detailed report about what's happening with your app. So, and we actually run it on a wide range of devices of Android phones, so that we know that these devices cover like most of the crashes and most of the other kind of issues. So we know that by just running through that, your app will actually have been tested without you having to do much. So we give you information about crashes. So we'll tell you which devices your app is crashing on versus which devices it's not. We'll of course give you stack traces and logs of whatever we have on our devices so that you can debug those crashes. A lot of the device-specific bugs also happen because of internationalization, and they happen because of screen densities and layouts and things like that. So we'll also try and give you a auto-generated list of screenshots where you can actually find layout issues. This is actually a real example where because of German and Italian translations, the app was really not working. They had a bunch of text hidden, and the developers were able to actually catch it and fix it. And this happened only on Galaxy Note devices for some reason. We also do a deep security scan of your app. So malware on mobile apps is a pervasive problem, mostly because oftentimes app developers use libraries that were built by other folks, and those libraries might not be the most trustworthy ones. So accidentally, you might be incorporating malware into your apps without you wanting to do that. So we use the same security analysis that Google uses for its own platforms, and we do that for your apps on the Play Store. And we'll actually flag you a bunch of security issues, whether you are doing things in an unsafe way, or whether you're using things that have known malware signatures. We'll actually flag you and we'll let you know about that as quickly as possible. So we've had pretty good success with just this, right? Like, so the whole reason why we want to do this is because we want to really bring up the quality and the stability of the entire ecosystem. That's why we're investing so much money and time and effort into this. And the early results are very promising. in just about 6 months since we launched, we've actually seen 20% fewer crashes for apps that actually use the Play Launch report. So if we take two apps, one of them doesn't use the pre-launch report, the other one does. The ones who do see 20% less crashes. It's still a bit of a confirmation bias right now because the apps who tend to do it are also ones who do really care a bit more about testing. But over time, we're seeing these numbers stabilize. So hopefully, these patterns will hold. The other stat which was really promising and encouraging for us is, and this is how we actually know that app developers are really taking advantage of the Play pre-launch report, is if you had a release and you released it to the alpha or beta channel and we sent you an email saying that, hey, look, you guys had crashes and your app's not performing well on these devices, we see that 60% of those crashes are actually fixed in the subsequent release by the developer. So you release something to the alpha beta channel, you get a report, and you have fixed it before it's widely available to everyone out there. That's the exact desired outcome that we want. And I think our goal is to try and push that number as high as possible, as close to 100% hopefully as possible. So far we've seen great uptake here and really happy about that. I want to switch gears just a little bit to crash reporting. I know it's not exactly in the realm of testing per se, but we think that by working closely with app developers and by engaging them through the entire app's lifecycle, we can actually have a positive impact on software quality and app quality. And we are firm believers in helping app developers closing the loop. So our goal is to make sure that these things work seamlessly as much as possible. So we took the same principles of simplicity and user experience, and we brought them to crash reporting as well. Because face it, even if you've done a good job of testing and you've used the test lab to its full potential and you've written tests, there's probably going to be some arcane issues that you're going to only find because you didn't think of them or you couldn't anticipate the environment changes. So we as a part of the Firebase SDK, we actually include crash reporting. Our goal is to give you not just data, but we want to give you data that you can actually take action on and help fix bugs as quickly as possible. And then hopefully you'll use our test lab to actually write tests and not have those bugs in the future. So it's a very easy setup. You integrate our SDK, you do a one-line initialization, and that's it, you're done. Once you release your app, you're going to start seeing crashes right away. And that's great because people want data as quickly as possible. They don't really want to do complicated setups for something simple as crash reporting. This works across both Android and iOS, so we're kind of trying to engage all app developers here. We've used Google's proprietary algorithms and expertise in trying to figure out which two crashes are similar, and we actually use that same technique to cluster crashes and crash data and make it available to app developers. So even though the stack traces might be slightly different, but they are the same root cause, you'll find them in the same clusters. So you don't have to waste time going through like 5 stack traces and realize that, oh wait, they were basically the same issue. We try to do that for you as much as possible. We've been using this infrastructure internally for quite a few years, and I'm really happy that we were able to bring it out to the wider developer community as well. We've invested pretty heavily in user experience. We try to keep the UI as clean and as simple as possible. Again, developer experience really matters. Nobody really gets out of bed wanting to look at their crashes, but at least when they're looking at it, they should not, they should have a good experience, and like it should be easy to use, etc. We try to also highlight the big picture of what's causing the crashes and where exactly these crashes are happening. So we'll try and isolate by phone versions, we'll try and isolate by operating system versions, other environment issues, just so that you can quickly get to the root causes as much as possible. Not only that, we've actually and this is where one of our innovations really comes into fore, is we actually work really closely with usage analytics so that you can actually get some repro steps leading up to a crash. Because how many of you have debugged a crash report before, but you didn't know how it actually got there? Few hands, okay. it's really painful. I mean, really, sometimes you don't know what the user actually did. So what we've done is every time we actually see a crash, we also take the entire buffer of what the user had done in terms of the analytics, because people who use Google Analytics also use the Firebase SDK as well. So we can actually log those same events with the crash. So we actually know what actions the user had taken leading up to a crash. So we know they opened a certain activity, they swiped somewhere, they clicked on some elements, and we can cluster that data along with your crash report. So you can reproduce and debug these things better. Again, as I mentioned, we try and really bring out as many environment variables as we can, so that you know if there are any particular correlations you need to take particular things into account. Does this crash happen only when I'm charging versus when I'm not charging? Does it happen on Wi-Fi, or does it happen on mobile networks? Like, giving you that data really helps you fix these crashes really quickly. By default, we have a pretty powerful crash logging mechanism, but we also have custom logging. So you as an app developer can log additional things along with your crashes, so that you have more breadcrumbs and data to play with while you're debugging crashes. Just another screenshot of our logs. I'm just not going to talk more about that. This is one thing that I would really want to emphasize on. So what you see behind me is actually a graph of usage analytics, like how much money your app has made over the past few weeks, et cetera, et cetera. But what we've done is we've actually married the crash data to your analytics data. So people here who've been testing, and you filed a bug because you saw a crash, and how hard was it to convince your PM that this was actually a bad bug that they should fix? Like, because should it be a P2, should it be a P3, should it be a P1? Like, what should it be? And many people have this experience where they just don't know the impact of a crash. Like, is it something that it's a crash but nobody really cares about it, or it's a crash that's going to cause a rapid decline in your app usage and your retention and those kind of things. So by trying to highlight that data, by trying to get that data out there to app developers, we think we can help them prioritize bugs better, so that they know which crashes they should be focusing on, because they know which crashes are now causing big drop in engagement, big drop in retention, app installs, etc. And we have all that data that we can neatly tie a story around it. So they can focus on solving the most bad crashes first, and then sort of go down the stack. Here's an example that people actually use, something like that, where the value of closing the loop is really important. It's you're an app developer. The people who spend money in your app are your live stream. Basically, if you lose them, you're going to lose revenue, and you're going to go out of business really quickly. And for folks like that, they now have the ability where you see a crash, you know which users saw a crash, you can actually fix the crash and then sort of send them a notification and a credit based on the fact that you were able to fix that crash. And because it's all sort of built around a usage analytics framework, you're all working with the same, it's the same data set. So you don't have to go and sort of do custom analysis. It's just baked in there for you, and you can actually work with those audiences and those filters that are automatically created for you. So by making it really easy to close the loop, you can actually have a big impact there. So I want to spend a few minutes talking about a bit more forward-looking things, where sort of we see the trends heading forward, and how collectively as a community we can work on this. So number one, I want to talk a little bit about machine learning. We are right now living in a golden age of machine learning. It's progressing so quickly and so rapidly that it's things that seemed impossible a few months ago are just very easy today. Like a year ago, nobody thought that computers could beat a human at a game of Go, which is like an ancient Chinese game. But yet, we were able to do that a few months ago. And the power of like image classification and image learning and things like that has significantly progressed in the last year. And as more and more of these things are open source and available on cloud and other things, these are just going to progress at an even more exponential clip. So my challenge to you as a community is, how can we actually harness the power of machine learning and bring it to testing and software quality? Like, how are we effectively teaching machines to detect things that are undesirable behavior. So if, how are we teaching machines to actually spot mistakes in your code or in the way you're developing software? Can we effectively use these machines to build assistants for you who are watching you from behind your back? They're your pair programmers. They're your code review buddies. They're your testers. And you can. How are we actually sort of building this power into our development workflows? I can guarantee you that the solution that's going to win in this particular field is going to be the one that actually gets the user experience just right, because there's a lot of interesting papers and algorithms and sort of approaches out there, but in order to really make a difference here, the user experience is going to be critical as well. So how well you actually blend all that power into your workflows and how you sort of seamlessly advance that forward is going to be actually critical to solve these things. I also think that we don't really exploit and invest more of our compilers and tool chains. We have really great ways of optimizing apps and building and deploying things, but as a software testing industry or as a software engineering practitioners, we don't really harness that power as much as we could. And I think there's a ton of innovation that we could be doing in terms of static analysis, dynamic analysis, code generation, code optimization, and more. And I would really like to see the community rise up to these kind of challenges going forward. So you probably, if you weren't sleeping through the presentation, you probably remember this graph before that I talked about at the beginning of the slide. The reason why I bring this up again is look at the difference in slope. Mobile caught everybody by surprise, including us at Google, even though we own one of the most widely used operating systems in the world. It caught us all by surprise, and the growth has just been staggering and exponential. It's now that we're sort of trying to wrap our head around the explosion of mobile and trying to, as a testing industry, we're trying to sort of come close to fixing some of these problems. We're not quite done yet. It's going to take a few more years to get there. But the last few years have been fairly painful for those of you who have worked on mobile. So I don't have a crystal ball, right? Like, I don't know what the next big thing is going to be. I don't know if it's going to be augmented reality or virtual reality, or is it going to be assistants, or is it going to be just AI in general, or is it going to be self-driving cars, or is it going to be wearables, or Internet of Things, or things I don't even know about, right? But I can guarantee you that the next slope is going to be even more sharper than this in terms of the way it will get adopted, just because a larger share of humanity is now primed for adopting new platforms. So let's not repeat the mistakes or the things that we did on mobile for whatever comes next. And that's all I have. Thank you.
Excellent. Thank you, Niranjan. And thank you for leaving plenty of time for questions, because we've got a lot of them, which I have here. Yes. Test lab run tests on real device or simulator?
Both. You can choose either. It costs about $5 to rent a device for an hour to run your tests. It costs about $1 to rent a virtual device or an emulator for your test. So we support both.
Good to hear. Are you also working on something which helps test end-to-end client-server test apps? Are there any frameworks to do so?
That's a great question. We did think about it quite a bit in terms of our roadmap and other things. Unfortunately, that's one of those things where these are so heavily dependent on the topology and the software architecture that a particular app is going to use. So it's really hard to generalize a solution for folks, but we're looking into it.
And any questions in the room, feel free to raise hands. I'll get to you right after I read this question. What about tools for iOS apps? What most app developers have to support Android and iOS?
We have heard this feedback loud and clear, and all I'll say is stay tuned.
Yeah, so we actually use the Play Publisher API to upload our APKs to the store, and We noticed that with that, we don't get the pre-launch check. Is there a reason that you guys?
Yeah, we're working on it right now. So because of reasons that have to deal with lawyers, we require you to check a box right now, but we are working on it.
Yes, reasons because of lawyers explains many, many things. And at any time, raise your hand if you have a question in the room. What initial setup do you recommend for a small startup that needs to start introducing automation into a project?
Wow, that's a fairly broad question.
Let's just list them all.
Yeah,
everything you need.
So, I mean, I would really, and those of you here at Google have heard me rant about this. Sorry, you have to hear this rant again. Number one, if you can unit test it. Like that's in terms of the return on investment, in terms of the amount of value you're going to get in return for the time you spent it. It beats anything else hands down. Even today, like the state of unit testing on mobile is nowhere as good as I would like it to be. Doesn't matter if it's inside Google or outside Google. So if you were an app developer and if you had to spend time, I would say if all you did was just unit tested really well, and if you wrote really well tested code with like good unit tests, and you used some form of a robot or a monkey runner to sort of get some device coverage, you're probably going to get a decent amount of coverage for a very cheap amount of investment. So that would be my recommendation.
Very good. Does the lab also test for geo-specific scenarios? For e.g., is there a way to run only on devices and networks in India or Mexico?
Another piece of feedback that we've heard loud and clear, so all I'll say is stay tuned.
That seems to be a theme. A speaker yesterday mentioned his team discovered differences between emulator and real device tests. Does Firebase Test Lab run on emulators? I think we already answered that. How does pre-launch testing work? Is it automatic monkey testing, or does it include some manual testing results? How did you detect localization problem?
So it's all automatic. There's no manual element involved here. We crawl your app and we'll analyze the data. In terms of localization problems, it's right now we just give you all the screenshots, and it's the onus is on you, the app developer, to actually find those issues per se, but we are working on automating that away as much as possible as well. We have some great screen diffing infrastructure within Google that we're trying to bring it out as a part of the test lab as well.
Okay. Can you exclude certain paths like the robot takes, like making real purchases?
Not yet, but we're working on it. So the way we are letting app developers do that is by actually providing us accounts that don't lead to any disastrous effect in your system. So it could be a test account that actually doesn't, like, even if you purchase, the purchase doesn't go through. But we are working on letting you isolate parts of the crawl tree better. So think of it like a robots.txt file for your app robots.
Other words, stay tuned. Is it?
Yeah, you can just answer those questions that way.
Not this one. Can you talk about efforts to bring test labs to classrooms?
So you can use Test Lab for free today. If you can get something like 5 hours of testing every day for free, and it's open to all of you. If you are in classrooms, if you are a student, you can just go to firebase.google.com and you can actually start using it for free today. So. And it's built in as a part of Android Studio, which is also free. All the material is published on the Android developer website, on Google's other website, and we are working on bringing some of the content over into Coursera and and Udacity and other things that I talked about earlier. So the tools are already available for free for you to use today, but we'll be trying to bring some of the educational content and packaging it in a more classroom-friendly way as well. But no, that's great feedback. Thank you.
Any other questions in the room? Oh, got one.
Here's a mic.
In the meantime, maybe you can answer Firebase or Sauce Labs. Which is better?
No comments.
You said you will dump the buffer when we submitting the crash data, right?
Yeah.
So how you deal with the privacy data? Should we consider about that?
Yeah, no, that's a great question. So we do a few things. Number one, we don't have access to the data. It's you, the app developer, it's your data. So in a certain sense, it's also your responsibility to make sure that you're not accidentally logging things that include personally identifiable information. Having said that, we try and take as much care as possible to actually scrub out things that we think might be offending. So we have things that, we have systems that look for patterns around credit card numbers, social security numbers, driver's license numbers, email addresses, phone numbers, etc. And we'll try and scrub them out of the logs as much as possible. So as a result, but we can't really guarantee 100% coverage there. So which is why we also, the app developers themselves need to be involved in this process.
Okay. Can Firebase figure out the memory leak on the background of the UI test? In Android Studio, we currently have to find out the leak by process ID.
So right now you can get a bunch of performance data when you run tests on the Firebase Test Lab, or even when you run them through the Play Store's pre-launch report. We don't quite yet identify memory leaks per se, but as standard refrain, we'll look into it into our roadmap. It's definitely one of those areas where we want to continue innovating going forward.
Will you ever allow plugins?
I don't know what that means, sorry. You can send me an email with more details. I can answer that offline for you. I don't know what plugins that you're referring to here.
My name is Theodore Chan. So I had a question for Firebase. You have tools for localization and geo with consideration for language, and then also bandwidth changing, or issues with variances in bandwidth and networking considerations.
So are you, is your question around libraries that you use while developing apps, or is your question around?
More for the tools you guys have for Firebase for geos and localization for going to different regions and languages.
But are you asking it as a person who's authoring tests, or as a person who's building apps, or?
Both for testing and then for development. If we have an app that's for North America in English, and we're adding Spanish and moving to other geos, what kind of tools does Firebase have some tools currently?
No.
Okay.
We don't. So we do things like it's most of the Firebase infrastructure is fairly locale agnostic. You generally don't the tools themselves are localized in all the languages and available in multiple different languages and locales, but we don't do anything specifically to actually support that. In most cases, those are actually handled by your operating system libraries anyway. On Android, you have your layouts that really mostly handle that, and on iOS, you have your resource files that do that anyway. So we generally don't have a common solution there yet.
The ever-present plea to improve the Android emulator.
So I want to give a huge round of kudos to the Android team. If you look at the emulator over the past year, it has actually improved significantly, and the Android team is investing a ton of resources in doing that. So yes, it's definitely happening. It's already improved quite a lot, and it's going to improve a lot more. If you have specific feedback about the emulator, please come talk to me after this. I'm happy to channel it to the Android team. But I know they're working on it feverishly. This is one of their top priorities.
Can we get the pre-launch report for every version submitted to the Play Store?
So we can't go back in history and give you that for all the older versions, just because we have to seek your consent before doing that. Lawyers get in the way. But you can get it for all future versions. So.
How about stress testing? Let me guess. Stay tuned.
Right. So it's actually, you can do that today. It's on you to write those tests to actually do stress testing. I mean, you can write tests and that run for an hour and stress out a bunch of things in your app and get all the data back. You can do it today, but we don't provide anything specific. You have to write those tests.
Available today. Very good. The differences from Crashlytics.
So first of all, I'm a big fan of Crashlytics. They're an amazing team. They've really innovated very heavily in the sphere of developer experience, and I must give them all the props and credits. The fundamental difference I think that I see is like we are very well integrated into the Firebase suite of things. So if you are an app that actually is using Firebase for other things, such as using backend as a service, or using our notification services, or our app distribution mechanisms or analytics, then you probably want to use Firebase Analytics. Crashlytics is pretty powerful too. I do think that our clustering is probably slightly better, but they have amazing tools and experience. Their setup experience is also really good. So it's, yeah, I mean, if you're using Firebase and using Firebase Crash makes more sense. But we have a lot of people who also continue to use Crashlytics side by side, and that's fine by us.
I guess skipping one, staying with crash reporting, how about criticism?
Same thing. I think the Crashlytics right now has a far higher market share than criticism. But I mean, yeah, it's a crash reporting service. You should use one that makes most sense for you from your developer workflow. How much do you care about being able to tie crash data to analytics data and to other things? And if you want that, then use Firebase. If you want the other features, use criticism. Really, like they're mostly at feature parity in terms of just the bare bones crash features. Like you get a crash, the crash gets sent up, it gets clustered and analyzed for you. So the basic features are the same.
Oh, and I didn't mean to skip the one that was before that one. So if there's a way to get it back, or if somebody wants to ask it in the room. Oh, is it here? Okay. Can we find out the list of tests being run in pre-launch test are all selected for all types of apps?
So we don't actually run, like there's no list of tests that we run, right? Like there's we crawl your app and we'll try to uncover things along the way. Our crawler doesn't really know anything about your app, so we don't really have like a pre-canned set of tests that we want to run on your app. And then we try to report data around crashes, security issues, layout issues, etc. So you can definitely see all apps get the same treatment, really. So
What platforms are supported and how it's avoid false positive?
So I'm assuming this refers to the test lab crawlers, this particular question. So it supports Android versions going back a few releases up until KitKat, I believe, maybe even a couple releases below that. We support different form factors. We support different OS variants, hardware manufacturers, etc. In terms of avoiding false positives, really, if we see a crash, we report that crash. So there's usually, in cases of crashes especially, there's no false positives generally. Like we know you kind of crashed because we see the crash.
Hi, I'm Usman from BlaBlaCar. I had a question about the crawler again, the app crawler. How well does it perform on different kinds of apps, such as games that have no real menus? And
So
smart? Oh, sorry.
Games has been a very challenging. Sorry, I didn't mean to interrupt you. My bad. Games has been a very challenging thing for us, mostly because the crawler has no way of knowing the gameplay mechanics. So we are trying to figure out how we can work with game developers here. So a lot of game developers actually have demo modes or sort of like pre-canned modes that you can go through games that they use for testing their graphics or their physics engines or things like that. So we need to make sure that our crawlers can be fine-tuned towards that a bit more. But it's a pretty hard problem. It's a work in progress. Like we don't have anything to announce immediately on that. But that's a great question. It's pretty hard to come up with an answer for that one.
Thanks. And the second part was, can it be made a bit more intelligent by just seeding it or allowing app developers to seed it with some actions that are coming from real users or from themselves?
Yeah, so we are working on that, yes.
Thanks.
Performance and security.
So I think I answered the performance question earlier. It's up to you. You can always write a test that stresses the action multiple times on your app and get performance data for your app. In terms of security, we can give you, like, you get the security report through the robot run right now and the pre-launch report. But if you can always do more security tests if you really want within your app. You have the power of writing Espresso or Robotium or UI Automator tests and doing that yourself as well.
So software development being more accessible, free education tools, blocks. What is your perspective on the impact on quality software?
So
testing for accessibility, I suppose.
Yeah, I think in general, I think the quality hasn't really kept pace with the growth, and that's pretty evident. And I think you saw the stats earlier in my slides today, where we actually did an analysis of the one-star review apps with one-star reviews, and it was really eye-opening when we did that analysis, where the long tail actually has like pretty high amount of crashes and generally quality and stability issues. So yes, it's a problem, and hopefully we presented a couple of our efforts that are helping solve this, but we are no way close to done. Like, I think it's a long road ahead for all of us.
How about Xamarin? Do we work with that?
So you can definitely deploy the apps that have been built using Xamarin on the test lab. Also, I think Xamarin now has their own test lab, I believe, if I'm not mistaken. They were acquired by Microsoft, and they have their own test lab. Or maybe I'm missing things, but they also have something within their developer environment as well. But you can, like, if you have an Android app that was built using Xamarin, you can actually run it on Firebase Test Lab today.
Hi, Caden from Busy. Mobile apps that usually deal with persistent storage have to test data migrations on updates, and I was wondering if the pre-launch report tests from the previous version to the latest version being installed on top of that, or if it's just a fresh install.
That's a great question. It unfortunately, because of security reasons, we have to do a fresh install. So what we do is, after every test run, we actually wipe the device clean, we reinstall the OS image, bring the device back to a previously known good state, and then it's a fresh install. The security challenges make it really hard to deal with that a bit more. But we are hoping cases like those, you can actually do it through your own custom tests, where you could actually install one version and then another version by writing custom tests.
Do you ever think Firebase will ever allow us to run unit tests on real devices? Similar to how you can run JavaScript and tests in browsers.
So I'll just do a little nitpick here. Technically, unit tests, you should not really be caring too much about devices. Unit tests are just testing a small piece of code in isolation. On Android, I'm a big fan of Roboelectric. You should just use Roboelectric as much as possible. It's amazing. It's the best thing ever. So having said that, you can run any test on a test device. Like, we support JUnit, we support Espresso and other things. So yeah, you could have a JUnit test running on real devices today.
How about automated accessibility testing?
It's definitely in our roadmap. In the pre-launch report, we want to sort of try and highlight some of the things as well. So stay tuned, I guess.
Do you have any data correlating the quality of developer experience to the quality of applications built?
Unfortunately, we have the correlation on the other side, where by engaging with developers as much as possible in their workflows, and by really improving the experience, we see a positive impact on quality, but we don't have data that goes the other way at the moment.
Do you need to provide credentials to access the app to test?
No, you don't need to, but if you can, then your app, we can do more with your app.
How about penetration testing?
we don't do a whole lot of penetration testing. We do a whole bunch of basic security crawls, looking for things like you're using a HTTP stack that we know has bugs in it, or you're doing data marshalling in an unsafe way that we can detect by looking at your app's signatures, etc. But beyond that, we don't. A lot of the other penetration testing actually requires manual intervention and input, and we're hoping that over time we can use machine learning and other things to help with that. I think last question, or we're kind of out of time, or?
They keep coming in. You're stimulating even more questions.
Right.
But yeah, we'll take say 2 more. When Espresso will be more flexible to write tests to switch and get full access of the device and its pre-installed apps?
That's a great question. I know the Espresso team is working on it and it's on their roadmap. I just don't know where they are with respect to the release timelines, but it's something definitely that the Espresso team is working on pretty heavily.
All right. And finally, if my app requires interaction with other nearby devices with the same app installed, can I use this framework to test my watch app,
Unfortunately,
for
not.
example?
Unfortunately, not yet. Just because when you have about a few hundred devices shoved into a same rack, we have extreme amount of challenges with Wi-Fi interference, with other sort of isolating radio signals, etc. So adding Bluetooth to that mix, for example, would make things super hard for us. So at this point, unfortunately, we don't have a good hardware solution for you to do that yet.
Okay, excellent. Yes, I think I will spare. Was there one more in the? All right, one more in-room question.
Are you leveraging a WebDriver for your UI interaction or a proprietary approach?
So we use Espresso basically for all our UI interaction. For native apps, we don't really use WebDriver, and Espresso is open source, and it uses the basically the open API within Android for accessibility API within Android for traversing the UI. So we use open source technology.
Thank you, Niranjan, for taking the onslaught of questions.
Thank you.
Excellent keynote. Next, we have Jerry and Guobing. I hope I pronounced it correctly. They're going to talk about Docker-based Geo dispersed test farm.
Yeah.
Got the control.
Yeah, thank you.
Good morning, everyone. My name is Jerry Yu. I'm the software architect and also managing a team responsible for test integration and test infrastructure in Open Source Technology Center in Intel. So the organization I'm working for is named the Open Source Technology Center, which is the heart of all open source development activities in Intel. So we are working on, Linux kernel, graphics driver, virtualization, OpenStack, embedded Linux. So if you know it, that actually Intel is the top 1 Linux kernel contributor in recent many years in terms of both the lines of the code and the number of the patches. So that's most of those come from our organization. So today we are going to share the test infrastructure practice in Intel Android program, which is also one of the system engineering projects we are doing in Open Source Technology Center. So Guobing will present together with me. So Guobing will.
Yeah, hello everyone. My name is Guobing Chen, and I'm from the Intel Open Source Technology Center as the QA architect, working focusing on the power and performance, and also automation. Yeah, thank you.
Okay, good. So it's good to have this chance to attend this conference and to not just share our practice. It's actually a good chance for us for me personally to learn a lot of good practices from youth workers in your companies. Actually, I already got a lot of resonance from the talks yesterday, because we share the same pains and share the same challenges actually in our project. So I hope you will get the resonance from our talk, and then we also would like to hear from you, and then we can discuss and get a better idea to make our work better. Okay. Okay, I'm going to talk a bit for the challenges for the system product engineering regarding the test infrastructure. So, which will usually translate to the general requirement like a test as a service from the engineering team. So we will elaborate a bit what's our understanding regarding the test as a service. So then I will introduce a bit our test infrastructure, how Docker technologies play the role in our test infrastructure. Then I will talk a bit the test distribution or test dispatch mechanism in our test infrastructure. So after that, I will pick up a few examples how we handle the technical challenges in order to achieve the test as a service vision or requirement. Okay. Okay. This table provides a definition of several terms I'm going to use in our talk. So I'm not going to read it. I will pause here for 10 seconds. You can read it. Then you can understand the language we are using in the coming 20 minutes. Okay. Okay. We start with the challenges in the system engineering project, right? About testing, what challenges we have. Actually, I would like to correct a bit for this page. Actually, the first two bullets are really talking about the challenges in big system engineering, which will involve hundreds of developers, engineers, involves geo-dispersed engineering teams, right? So the first one is about the device sharing. We are doing product. Before that, what we get is the development vehicle or engineering sample, right? We say it. So it's always difficult, or I would say it's not able to provide the one device per engineer for a bigger engineering project. Okay, so the program manager will always get a much larger number than the program can offer regarding the engineering samples. So for that will require us to maximize the device sharing for a specific purpose, for example, testing. Then we are always required to maximize the device sharing for testing purpose, no matter what the testing is for, right? No matter it's QA testing, CI testing, DevOps testing, whatever. The second one, the same thing. The first one is about hardware. The second one is about software, right? We have a lot of automated test cases created by QA, by developers. So the challenge is it's those test cases most of those are limited to the experts or owners who know how to run that, right? So then we have a general requirement that can we enable other users to run those test automation, right? Not just the one who create that or the ones who are responsible to run that, right? So the last one is, assuming we have a test infrastructure to support both, then we also needed to think about how to to lower the maintenance cost. If you think about it, if we have hundreds of test benches in our test farm, we needed to think about the maintenance cost, right? So this is the general requirement, or we translate the test infrastructure requirement from engineering teams to the eventually, it's something we need to provide a test as a service, right? So we have actually, usually something as a service. The spirit of something as a service is really to enable the users to easily to do something, right? So, when it comes to testing, it can be abstracted to a general requirement that we name it here. Basically, okay, anyone can run any automated test cases on any device, anywhere at any time, right? So this is the vision of the test as a service we understand, So the testing infrastructure will play the critical role to achieve above objectives. Okay, before I move to talk our test infrastructure, I would like to talk about the audience of our test infrastructure. The first one is definitely the CI infrastructure, right? So it's fully automated to do the pre-commit, pre-merge, post-commit testing, right? When the patch come in for review, the automated test will be triggered automatically to verify the patch is good or not, right? We need to verify that on all the available target platforms. The second one is the QA testing, release testing. So for this type of testing, usually we will almost run all the available automated test cases on the target platforms. It's manual triggered, and it also can be configured as automated trigger. One usage worth mentioning here is the failed test cases rerun. This is something actually John and the professor talked a bit yesterday about a flaky test, right? Actually, we had the same issue. We have the same problem. Actually, besides the flaky test, because we are doing the product, so we also have the flaky test bench issue. Okay, so basically, but no matter it is flaky test case or flaky test bench, for QA they will need to rerun, right? So the test infrastructure will need to support testers or QA to run the failed test cases efficiently. Okay. The third usage is developer testing. Developer testing, they will, they will run the selective test cases or domain-specific test cases for their domain only, right? They usually test against the build they manipulated, created themselves. The other user story here is they will also have their own developer tools like digital OMI check or bisect check for regression check, right? Where they will also need to do the testing. So their tool will connect it to our tool test infrastructure to offload the test to the test infrastructure. Okay, this is the overall deployment diagram for our test infrastructure. You can see, we have basically a worldwide single master running as a service entry portal to accept the test request from different front ends. So all the services we exposed as the RESTful APIs. Then, different front ends can, trigger the test request through those APIs. For the front end, we have several types of front end. One is the CI system, right? It's easy to understand. We also, for QA, we also have the web UI portal, which enable the testers to define the test job and trigger the test request. We also provide the command line to trigger the test request to our service. Those command line can be used to integrate together with developer tool to fulfill their testing needs, right? To offload the test to our test infrastructure. So at the back end, you can see, this is our device farm, our test farm. So the key idea is here is we have the test slave host, which is basically a PC. In our practice, we are using the very small form factor computer NUC and next unit computing. I'm not sure if you know that Intel produced this kind of just this kind of size, very small, but it's power enough to carry on the test. So each test slave host will connect to multiple dots. So for each test request, when it comes in, when the system identifies the right test bench to run the test request, a new test Docker, appropriate Docker image will be spun off to map the device to the Docker, to map the appropriate test equipment to the Docker, then we can run a test. That's the basically that's the whole idea. So you can see, for the test slave host, there is no any dependency you need to install. You can just install a vanilla Ubuntu, for example. The only prerequisite is the slave host, the OS can run the Docker, right? That's all. You don't need to install any dependency there. That will, as what I said, mitigate or significantly reduce the slave cost when you have hundreds of test benches. So the other one is the, because the test farm is geo-dispersed. We have the device in Shanghai, we have device in US, we have device in Mexico, we have device in Romania. So we have to speed up the image downloading and the other test data and the test artifacts downloading. We have the geolocal artifactory mirror to speed up that. This is I would like to for test distribution. I would like to talk the key idea here. We have a test catalog database. We call it a test case catalog or test campaign catalog, whatever. Basically, this database records the information like, okay, what for test campaign, what are the kind of capability needed in order to run this test campaign. Like, okay, I need a power meter, right? I need a monsoon power meter, or I need a USB cutter on the test bench. I need a I/O relay card, something like that. Besides of that, we also have the information like the best case of the execution time of this campaign, the worst case, the average time, right? Something for us to schedule the test request appropriately. This is the test campaign part. The device part, you can say, okay, basically we will log the information like, what kind of capabilities this test bench has. The same thing, will you, power meter, USB cutter, basically identify the capability, the campaign this test bench can to support to run. Okay, So for distributor, besides the regular sharding mechanism, test sharding mechanism, load balance mechanism, the key idea is we match the capability between the campaign and the test bench, then do the appropriate distribution, test request distribution. Okay, this I would like to give the some examples how we address some technical challenges in order to achieve the test as a service we mentioned previously. So the first one is we need to provide any device anywhere, right, to user. That means, okay, the first one is, for our test infrastructure, we should be capable to control the device and control the test equipment remotely, reliably. Okay, so at this point, in our practice, we introduced a lot, equipment. The major one is our relay card. We create it. We design this board and create it ourselves. Basically, you can understand this will relay the signal. The device the test device under testing will be reworked, and then we will connect the power, like a power button, volume up, volume down, to this I/O card. Then we can we can mimic the user intervention, like push the power button 3 seconds, push the power button and volume up at the same time, something like that, right? Then with that, you actually can, control the device no matter where it is, right? So actually, in our infrastructure, when your test request is dispatched to run, then you actually get a remote shell you can log into. Then you can control the device actually. The second one is the state transition management, because because everything is the whole workflow is fully automated, right? So we needed to think about the state transition, device state transition. So for the because we will, every time we do the test, we will need to flash the device, right? Burn the image to the device. During that, device will on off several times. Because the device is allocated to container, when the device is off, actually the container lost the allocation, lost the connection to the device, right? Well, so when the device is up again, you need to think about how to get the device back to the container again automatically. So generally this is done by the UDEV roles. We added the UDEV roles on the host machine, which is actually automatically generated at the UDEV script configuration file. So when the device off, we will remove the node in container. When it's back, we will add back the node to the container. So basically, it's work like that. So I just give an example. Here we have some technical challenges in order to to enable the user be able to use the remote device, run the test, just like use the device at their desk, right? So, okay, I will give it to Guobin to talk about how we leverage Docker to manage the test case, release the test case. Okay.
Hi, I'm back. So thank you for Jerry to sharing the background and the big picture of our solution. And I will talk more here about the Docker part, why we use Docker and how we use Docker. So firstly, I have a question that how many people know what is Docker? Maybe? Oh, a lot of that. So yeah, it's great that we have lots of participate on these new things. That's good. So for those who never know this kind of things before, a brief introduction about Docker is that it is the open platform for application packaging, distribution, and deployment. So, but what I will tell you that about the Docker is that firstly, it is compared with the traditional virtual machine, this kind of the technology. The first advantage of Docker is that it is very lightweight. So, for example, on a typical desktop like the NAC, the small NAC, usually you can only run like the 2 or 3 virtual machines like VMware or virtual PC, this kind of the virtual machine instance. So if you exceed this kind of amount, your NAC will most probably will start, because it will consume a lot of the resource on the system. But with Docker, the things will be quite different. So usually you can launch like the 16 or even 32 Docker instance in parallel. So in this way, you can save a lot of money to have much less host needed for your testing. So that is the first thing. And the second is about the packaging. You know that for Docker, actually, it built it built upon the Linux container, and it will help you quite easy to package this kind of thing. So as a test case developer, you may not enough to just give your test case to your developers to run it, because he also need to package all of the test environment and a lot of dependent library, this kind of thing. So with Docker, you can easily to package this kind of thing in a single binary, so you can directly run this Docker image on your host machines. So that is the second thing. And third is about the hierarchy, which I show the graph here. You can see that Docker support Git like the code maintaining. So we can maintain our code like hierarchically. I think people who are familiar with the C++ or Java, this kind of the object-oriented programming language, will be very familiar with this kind of thing. So you can see that we can have the first layer to people working just on the basic libraries, and his library, his package, his Docker package will be inherited by the second layer about maybe like the test infrastructure guys. And the third layer may be the test case developers. So you can see this kind of inheritance by the way. So and even within the third layer, you can also different test case domains. You can develop in parallel to do the packaging separately. So that is the good thing that we why to use Docker and how we use that. Yeah. I think that's all for the Docker thing. So, yeah, I think that's all from. Yeah.
Excellent. Thank you, Jerry and Guobing. We do have a lot of questions, but I just wanted to say I liked how you narrowed down the problem to just anywhere and at any device, anywhere in the world, at any time. That
Thank you.
Really compartmentalized the problem. So for questions, do you use any orchestrator, e.g. Kubernetes or
No.
Docker Swarm?
No, not yet. Actually, the way we use Docker is it's a native way to use. We didn't use those orchestrator to do that. Yeah.
Fair enough.
Yeah.
Is this available for people outside of Intel Group org to use it? And if yes, then could you share the GitHub location?
We do have the plan to think about which piece of the infrastructure can be ready to be open sourced. The problem is not it's a business thing. The problem is some logic is very close coupled with our the way how we do our product, right? The engineering process. So it's really coupled with our engineering process. Yeah. But yes, because at least as a service, as we are thinking about to host the same infrastructure to support other open source projects we are doing in Open Source Technology Center, because we have a lot of projects are developed in the community. We do have the similar needs from community users to because we have many devices, many machines, the developer will not have, right? So we need to think about how they can leverage. So.
Okay. Any questions in the room too? Just raise your hand. What test management software are you using for your test catalog? We use the enterprise tester, you might know that, as the static test case script management tool. But for the test case catalog itself, actually we created a database schema ourselves. But we do dump the data from enterprise tester to generate the schema what we need for our tool, right? So yeah, we use the enterprise tester. Test case owner maintain those metadata in enterprise tester, then we will periodically dump those data plus some other data we needed to generate the database. Yeah. Oh, question in the room, but I'll ask this first. Do you monitor device health, like flaky or failing hardware?
Right, this is a good question, because due to the time limitation, I didn't dive into that. The key technology we created for our test infrastructure is exactly the heartbeat mechanism. So in as what I said, the heartbeat, the heartbeat depends on what you are heartbeat, right? Heartbeating. So what we need is not just the device is there, LS, USB, the device, USB device is there. What we need is the device either in, take Android device as an example. The device must be either fast boot connectable or ADB connectable, which means we are able to burn the next image, right? So if not, then we will try the mechanism like, okay, can I, get it back to try to burn a golden image, which is, we know, always good, right? To get the device back into good shape. If we tried all the mechanism, all the method we can imagine, still not work, then we'll tag the test bench as unavailable state. That means a manual intervention needed to be engaged. Yeah. Yeah, and so we have this mechanism.
Hi, I wanted to sort of ask about your experience. Is it per job you send in one Docker image with all the code in, and you reset everything? And is that the reason why it's helpful for you to know that the cache is clear, everything is clear?
Yeah, that is one of the major purposes that why we use this kind of the virtualization to clean the.
And what is the cost of that virtualization instead of
it's
just
very
cleaning?
lightweight, just as I introduced. It's very lightweight. You can run on the NAC. You can run the more than 16 if you want.
And then, so in terms of you going and cleaning the cache yourself versus relying on the Docker, did you see any significant increase in your time, or that wasn't the case?
No, because in our scenario, our testing actually happened on the device, not on the host. So it does not actually care much about how, because it cares, but not care so much about how the host performs, right? Because as I said, the Docker is quite lightweight, so it may be costing the millisecond, but that does not care. Yeah.
And if you want to scale this outside, let's say not just hardware, but let's say desktop code, do you guys have any plans, or have you guys experienced that kind of stuff? For hardware, I understand it's kind of it really helps for you guys, but if for a general build on a desktop, is this scalable in there as well?
Sorry, for which purpose?
So for example, you can send something to GitHub, and the build passes for some desktop.
Yeah, that will really help. Yeah.
That will help as well, and like you don't foresee any like big time lags or something
Yeah,
like that.
yeah, sure. Yeah.
Cool. Thanks.
Great, and I think we are out of time, so let's give another round of applause for Jerry and Guobin.
Thank you.
Thank you very much. So we have a break scheduled right now. So refresh, recharge. We will start again at noon. If anybody has seen Joe Ethier or John Howley, the next speakers right here, we need to get you mic'd up. And tell them when it does come. this goes back, but. All right, welcome back. Hopefully that break was enough that you needed to make it through the bathroom line. We know they've been long, so we apologize for that. So we are going into another hour of talks. We have this presentation and then 2 lightning talks, and then we'll go into lunch. So just another reminder, find the group going to the cafe you'd want to go to today for lunch, meet up with them, and now we have signs. It's improved. Ari is showing each time it gets better and better. All right, so we have, my notes. We have Joe and John will be talking today about Open HTF, yes. So I will hand it over and let them take it away.
Okay, hi guys. I'm Joe. My colleague John is on the way. Hopefully his parts don't really start till the second slide or so maybe we'll make it. So I'm one of the current maintainers of OpenHTF. John is one of the authors of the original internal testing framework that OpenHTF sort of evolved from. OpenHTF is one of the libraries we use at Google to facilitate hardware testing. In addition to talking about OpenHTF, I want to touch a little bit on general approaches to hardware testing at Google, how that kind of shaped OpenHTF. And also want to mention, as the name suggests, OpenHTF is open source software. The URL is up there, github.com/Google/OpenHTF, so you can go check it out. If you do that, we have, at the top level of our repo, we have an examples directory. I recommend starting there. In particular, there's a script in there called helloworld.py. Check that out. There's a lot of inline documentation that shows you what's going on. That's kind of the basic example of a test script that you would create with OpenHTF. Okay, so the needs motivating OpenHTF sound pretty similar to the needs that would motivate any other framework that you might use for hardware testing. So you want to exercise a piece of hardware, whether it's like a phone or a head-mounted display or some other device, consumer electronics or part of some bigger assembly like a server or a piece of networking gear. You want to exercise that hardware, you want to take some measurements, you want to record those measurements into a log or a record as you go. And then at the end, you want to do something useful with that record, like save it to a file on disk, upload it to a server somewhere, something like that. And the whole point of using a testing framework to do this is to make life easier for the folks authoring tests. So in our case, that's mostly hardware test engineers. But I think I want to dig into that a little bit because I think it's subtle but important. A lot of the pre-existing tools at Google were kind of oriented towards a more software engineering heavy audience, even though they were ostensibly catering to hardware testing. But we wanted explicitly to make something that we could use to partner with contract manufacturers, vendors, hardware engineers, and hardware test engineers, and that would give these folks all an easy interface to focus on the parts they care about, which is test logic. Okay. So consider that for a long time, Google had built itself as a software company, and kind of still does in many ways too. One notable exception being the platforms team at Google, which is the team that designs the like data center infrastructure, servers and networking gear. But now, of course, things have changed. We do a lot more hardware. There's a couple examples up there. We have Glass, Daydream, we have self-driving cars, all sorts of different consumer hardware with the newly formed consumer hardware group. And so with all these new types of hardware testing, we found that all these different teams started forming their own tools. And they were all catering to different purposes. And we really wanted something that would be general enough to capture most of the use cases. So OpenHTF came out of a team that included both hardware engineers, hardware test engineers, and software engineers all working closely together. It was written and rewritten with non-software engineers in mind as the primary consumers. Specifically, we wanted to make something that would cater to hardware test engineers, electrical engineers, contract manufacturers, and vendors. And then over the course of a few iterations, it became more lightweight, more focused, and platform agnostic. Welcome.
Sorry, running a little late. Missed the introduction. I'm John Hawley. I was a member of the team that wrote the initial version of OpenHTF before it was open source and all that. So I still sort of co-maintain with Joe and run late to meetings. Yeah, so I can give a little bit more context for some of the sort of original motivation behind some of the decisions that were made. I'll let Joe continue.
Cool. So yeah, main takeaway here is proliferation of hardware projects at Google. OpenHTF came specifically out of the Glass team, and it came out of a team that was that had software engineers and hardware test engineers working together, which allowed us to create something that looks a little bit different than some of the other test frameworks available. And
notably, the need at the time was actually driven primarily by manufacturing. We were doing manufacturing locally in the States, and we're trying to be pretty scrappy about it and doing a lot of things ourselves. And there weren't really any internal test frameworks that ported well to the manufacturing floor.
Okay, so the solution we came up with is a Python library. We chose Python because most of our hardware test engineers write Python scripts already to do things like kickoff tests, analyze data, et cetera. And we made it a library because we wanted it to be a straightforward import, just like any of the other tools that are commonly already used in hardware testing, like NumPy, Pandas, Matplotlib, and things that hardware testing folks are already using in their day-to-day work. And like most Python libraries, it's pip installable. So if you have an internet connection, you can just pip install OpenHTF and start using it. Also, as a library, it makes it easy to integrate with other frameworks in terms of deployment, scheduling, and things like that. We don't really provide solutions for those things out of the box. We're focused just on the hardware test authoring interface. So with your test script being just a straight Python script that imports our framework, you can do all sorts of things with it. Embed it in other frameworks, use it in any scheduling system you want, deploy it any way you want to deploy it.
Yeah, so a little bit more about that decision. Originally, obviously, if we're just running our own manufacturing floor, we did have a full execution environment. It was the only thread that was running. We controlled everything about what was going on, including deployment to the machine, scheduling, all this kind of stuff. We can talk about that a little more later. But when we decided to open source the code, we decided to make it more of a library because that integrates a lot better with what other people are doing, right? We don't really want to have to take over and say, okay, this is, you have to sub-process call to invoke this or something like that, right? So this is actually a lot of work. In fact, Joe did a lot of the work on sort of tearing out some of the process-specific stuff and making it actually work as a library. So hopefully, we're hoping that this actually makes it a lot easier for other people to make use of it.
Mm-hmm. Okay, so I kind of mentioned our...
Oh, yeah, that's right. So I already talked about this a little bit. The manufacturing floor is sort of the original use case. Some of the constraints there that were really driving us were that we had operators using the stations, not test engineers, which is pretty common internally. You usually have like test engineers overseeing things. But we did have test engineers writing tests, so not software engineers. So we didn't want to go too complex. It was kind of a sweet spot that we really needed to hit there. In an automated lab, we typically have test engineers writing the tests and running them. So they'll usually actually be a little more comfortable with command line interfaces and things like that. Sorry, I forgot to mention manufacturing floor. To that end, we actually have an HTML-based graphical front end. So you don't have to use fully command line tests. The automated lab, typically you'll have more of a command line interface. You'll have jobs getting kicked off automatically by something, and you'll be outputting to some sort of data store or something like that. That varies sort of by use. Benchtop is a little bit more, you have engineers writing tests, right? And that's when the code gets really bad. But yeah, that's usually something you wouldn't have too tight control. You don't typically have like version control over your tests even. It's just like, I built some hardware, I need to test it or something. The last one, we don't really expect OpenHTF to be have a huge value add. You could just as easily write a little Python script that talks over a TTY and does your thing. But if you get used to using it or something, you could design an output module that outputs into a format that you like or something like that, and then get some code reusability there.
So the main abstractions of OpenHTF, the top level thing that we care about is a test. We have a class called test, openhtf.test. What you do is you instantiate a test object, and then you execute it by calling its execute method. Those tests are broken down into phases, which are kind of similar to test cases. Phases can be as simple as just a Python function. They're kind of the atomic unit of testing. And then within phases, you set measurements, which are exactly what they sound like, individual pieces of data collected during the course of the test. Sometimes you want to save an artifact like a JPEG or a WAV file or something that was generated during the test, and we have an abstraction called attachments to do that. Finally, we have something called plugs, which are the interfaces to hardware, and we'll talk in a little bit more detail about plugs in a little bit. And then output callbacks let you do something useful with the test results once the test run is complete, like save it to disk or upload to a server.
So notably here, the pieces that are up to the test author to implement are typically just the phases. Normally, you would have also some test engineers that are a little more comfortable with Python, writing things like output callbacks if you're outputting to some local data store, or you could even have upload via HTTP, HTTPS, whatever. And then plugs are interfaces to various hardware. We have a small set of base plugs. We'll talk a little bit more about them later, but typically you'd end up having an engineer also have to write a Python interface to whatever hardware it is you're talking to. A lot of things come with Python interfaces already, though.
Okay, so wall of text, I know. So this is kind of a distilled example of an OpenHTF test script. So aside from the fact that widget plugs is a fake module that I made up for this, this test would actually run. This is pretty much all you need in order to create and run an OpenHTF test. Main stuff here to look at is you import a bunch of stuff at the top. You define some phases. Phases are functions. The first one's a very simple one. The second one is a little more complicated. You can decorate those phases to declare what their inputs and outputs will be. And then finally, at the very last line of the text, you'd call test.execute to run the test. And that call to test.execute blocks until the test is complete and the output module is run.
Yeah, so the general approach here is we use decorators a lot in OpenHTF. It kind of makes it a little bit more declarative about what exactly you're going to be measuring in any given phase. The original motivation for this was we liked having, and we'll talk a little bit more about config later, but we actually have a key value mapping in a config file. It's a sort of a YAML file, and it lets you have some declarative stuff. But we found that putting a lot of declarative things there actually decouples it from the code a lot and makes it really hard to sort of visually track what's getting measured where and what's going on. So over the course of one of the iterations, we moved that to decorators, and now I actually really like how this turned out. We have pretty clear inputs and outputs, although here I guess they're in the other order, they're outputs then inputs. But they can go in any order, they're just decorators. And they're right next to the phase that's doing it. So it's still sort of on the test author to write, to split their test up into phases that sort of make sense. You could obviously just put all your outputs and all your inputs on one phase and have a 1,000-line Python file. I've seen plenty of those in hardware testing. But the hope is that this sort of enables you to break it up a little bit more sensibly and make it so that the next guy who comes and reads your test can say, okay, I understand exactly what these chunks are and what's going on.
So plugs. This is actually one area where we need some help from you guys, the testing community at large. So plugs are what OpenHTF uses to interface with hardware. We call them plugs because plugins we felt was too indicative of pure software extensions, and we liked how the term plugs called to mind physical hardware. Our desire is to have a large collection of these plugs available to interact with tons of different off-the-shelf test equipment. So anything from power supplies to oscopes to logic analyzers to sensors, whatever you might use in a test fixture when you're testing a piece of hardware. Right now, our collection is pretty thin. We have some Android-related stuff. We have an ADB plug, and we have some generic USB stuff in there. But mainly, we've been focused on writing the framework itself. And also, a lot of the plugs we use internally are wrapping proprietary internal hardware or otherwise not things that we can share. But we do want to increase the collection of plugs that we have to share. So calling on you guys to make contributions to our GitHub repo. And when you write plugs to wrap your test equipment, please consider contributing them back to us.
Yeah, so this has evolved a lot, actually, over the course of this is probably the single thing that's changed the most number of times in the many iterations of the project. I kind of like the plug thing that we've settled on. I think it's pretty good. We're sort of centering it around building from the bottom up, right? So we have plugs that support, USB, serial, some low-level interfaces like that. More complex fixtures that may have a few serial ports. We have a couple one-off instances of those. We're still working out sort of exactly what the best way to use plugs together and how they play nice like that. But we are slowly building up a library of useful plugs. And also, I mean, it's a pretty small wrapper. Basically, you have to inherit from base plug for internal sanity checking purposes. But a lot of pieces of hardware will actually have a Python library ready to talk to them. So this ends up typically being a pretty thin layer.
This is one more thing we want to show you before we open it up for questions, and that's the web GUI. So knowing that we were going to deploy this to places like the manufacturing floor where we're going to have operators interacting with it that aren't necessarily familiar with the command line interface or the test script itself, we wanted to provide an off-the-shelf user-oriented experience. So when you run these tests in a separate terminal from where your tests are running, you can invoke this web GUI as a runnable module with Python-M that starts up a web server that will automatically discover any OpenHTF test that's running on local machines on your local network, and will give you a visual representation of them with color-coded test phases and measurements, and it updates in real time so you can follow the test as it goes along. In this one, I have a test with the ID of foobar-baz, and then there's a couple of phases, and I've expanded the hello world phase so you can see the measurements inside the phase.
Yeah, so kudos to Joe on this, actually. The internal version had a sort of Google internal front end and all that, and was not portable at all. So he actually completely rewrote the front end aspect of the project to open source it. It does do some really neat stuff around, like discovery is just multicast-based discovery for a local network. These are things that actually come in real handy on a manufacturing floor when you've got a lot of testers out there, and manually managing a config file of what all their IP addresses are gets to be a lot of overhead, actually. Yeah, this is a pretty awesome thing. This is still sort of evolving a little bit. We make minor tweaks to it all the time, and get a lot of internal requests. We should probably start forwarding people more to the external mailing list so there's more visibility. But yeah, this is still growing a lot. So there's definitely feature requests are welcome and encouraged around this.
Yeah. So the test authoring API, like that wall of text slide we showed, is all pretty solid and shouldn't change too much. The web GUI is still being tweaked a little bit, and we want to add more plugs, and we're still figuring out some of the nuances around plugs too. The main test authoring API should be pretty stable.
I hope so. It's changed, I think, like 4 times now.
Yeah. I think we got the good version this time.
In about as many years, yeah.
Okay, so that's kind of all we had prepped. So let's open up the floor for questions.
Yes, thank you, Joe and John. And to be fair, by Google and California standards, John was not actually late.
Right?
Within
Especially
the margin
engineer
of
standards.
error.
I'm early for the next meeting.
Can this be used to test mobile devices' battery consumption during an application over a period?
You want to talk about monitors, maybe? That sounds like a good application of monitors.
Yeah, sure. So we have a little bit of an addition to measurements that we call monitors, and we found it's something that comes up a lot, actually, where you just sort of periodically want to check something and store those values in some sort of list or something. And so there is a mechanism, yes, monitors, that will allow you to basically say, you tell the framework how to take the measurement, and then it will just periodically do that. So you just, once you write the code to talk to the device and grab the battery level, then yeah, it's pretty easy after that.
Yeah, and it keeps running through the entirety of the test, right? Not just
monitors are currently just the phase. We're actually talking about making a mechanism for doing so over the course of a test, yeah.
Okay.
My question is, have you had any exposure to National Instruments LabVIEW product? Have you seen how they do it? And was that part of the evolution to where you got?
Yeah, LabVIEW, I have unfortunately been personally tasked with porting a handful of drivers, I guess you might call them, for LabVIEW over to OpenHTF. Yeah, LabVIEW is an interesting way of sort of making hardware software play nice, right? It's people who don't have a lot of software experience write tests, really, is sort of the target there. I found that it starts to blow up real fast when you get to big tests, though. You get the lines everywhere and lots of stuff to follow. So there's a place for each of them, right? I think they can definitely coexist. LabVIEW is great for like spinning up quick little things. Unfortunately, we don't really have any sort of way to automatically use LabVIEW drivers, which would be awesome. There's a lot of National Instruments test equipment out there, yeah. But we are working on it.
Yeah, we kind of wanted to be agnostic as to which test equipment you were able to use too. So didn't want to like bias you towards National Instruments stuff or whatever. Or when I say you, what I really mean is our audience of hardware test engineers at Google who use these tools. Wanted to let them go to whatever vendors they want, get whatever test equipment they want.
Yeah, really, there's nothing precluding you from running an OpenHTF test within LabVIEW, actually. You could write a block that would run an OpenHTF test, right? Which was sort of the neat part about removing the execution framework from OpenHTF. It lets you do stuff like that.
Good. Are there any plans to support gaming consoles, PS4, Xbox One, et cetera?
That's an interesting one. I actually don't know what that would involve. I'm sure somebody out there got really bored and wrote a Python interpreter to run on these things. So you probably could, yeah. The other approach would actually be to run the actual Python test off device, which typically is more what you see for mobile things. You want to run the test off the device because if the device dies, you don't get any logs. And then you just really need a way to talk to it, which I personally don't know much about the hardware testing of these platforms, but I would assume there's a TTY header inside or something like that for testing purposes.
Yeah, so I guess there's kind of two questions inside that. One was, can we execute OpenHTF tests on those platforms?
Yeah.
And the other is, can we use OpenHTF to test those? Kind of different answers, but if someone wants to write plugs to wrap those for testing those devices, that would be awesome.
I'd like to commend you on your use of different interfaces for different personas, different end users for the tool. I wondered how much you'd done in the way of usability or user experience design in designing those interfaces. What process you'd gone through for that?
Yeah, so internally we did have a UX designer sort of consult with us. He didn't necessarily design the whole front end per se. It was kind of, we were borrowing some of his cycles. So we haven't had dedicated UX resources on it, but we did have, we have had input from the one UX guy who was helping out. And we do actually have a couple teams are actually using the web GUI, right? I think
yeah, a couple
internally.
Mm-hmm.
Yeah, so we do have a fair number of users out there that have given feedback. So this was I think the second, third iteration of the web GUI.
Yeah.
Yeah, so we have gone through a couple iterations and had some rounds of like user feedback and things like that, and some pretty big features. History actually on there was a lot of work to do because we weren't internally tracking previous runs of tests, but it turns out for the web GUI experience to really work right, you kind of need to be able to see the last couple that ran. So we actually put a lot of effort into adding that in. So we've gone through a couple iterations of sort of user feedback, yeah.
But we're definitely open to more feedback too. So if you have...
Yeah, like I said, that particular part is evolving still a lot.
Yeah, submit pull requests to us or just even file issues with your suggestions and we'll definitely take a look.
Good. Can you give a concrete example where your framework was used and how it improved over earlier versions, if any?
This one, I'm happy to say we actually don't have enough time to go through all the examples of this. Originally on Glass, we had our contract manufacturer writing manufacturing tests, and this was very, very early on. And they had many hundreds of lines of script files of their proprietary internal language that for some reason they made up because there aren't enough languages out there. So that was actually the formation of the team that created the original framework. I was asked as a software engineer to come in and help out, and I looked at it and I was like, oh my God, what's going on? So I was actually given a couple people to work with, and we came up with a framework and had, I guess the most quantifiable improvement there is turnaround time on fixes. It used to take them at least two, and this is, keep in mind, local, take them at least 2 weeks to fix any issue, no matter how small. By implementing it ourselves and doing it in Python, we had turnaround times of roughly less than 24 hours on issues. It was a really big improvement. I'm trying to think, I'm sure there's plenty of other.
Yeah, I think the self-driving cars is another another good example of where they had a bunch of different disparate like internal tools and cobbled together scripts and stuff, maybe some LabVIEW thrown in the mix too even, and they've started moving stuff and standardizing on OpenHTF. So I think the main benefit they're getting from that is having the consistent output format for everything. So every test outputs a record that's in a consistent format. You can upload it to the same data system.
Mm-hmm. Yeah, the history of that, the two teams actually used to live really close together in X, Glass and Chauffeur, and so they saw what we were doing. We're like, hey, let's do that, and we're actually getting a lot of value add from it. So much so that they actually grabbed one of the guys from the Glass team who used to work on OpenHTF, or the internal version of OpenHTF, and he's now over there, helping them out. So it is spreading a lot. Internally within Google, there are actually quite a few teams using it.
All right, and I think we have time for one more. How does the framework communicate with the device? What are the requirements of the API that the framework drives?
Yeah, so plugs are very open-ended in that sense. So most of the plugs that we use internally tend to be wrapping, like a thin wrapper around some third-party or vendor code that either comes with the device or is some third-party library that already exists within Python for doing the hardware communications. And then the plug is the layer of abstraction you put around that interface to just pull out the functionality you want and make it easy for test flow to look clean and
Yeah, we've spent a lot of time, especially in previous versions, actually trying to get this to be a nice, clean interface and be uniform across all different types of hardware that you want to talk to. It turns out the hardware world is an absolute mess when it comes to interfacing with it and how you talk to things. If you're writing low-level board-level tests, you've got I2C you probably want to talk, serial. I actually ported a VXI11 driver over. I don't know how many of you have ever seen or heard of that. There are a lot of things out there. So. The idea is by having just a base class that you have to subclass, it kind of leaves it pretty open-ended. That's basically the only constraint. So I guess the second half here is what are the requirements of the API that the framework drives. There are no real requirements except that you subclass that base class. And that's mostly for sanity checking purposes so you don't accidentally do crazy things. Otherwise, it's if you can write it in Python, you can make it work.
Yeah.
And that may even actually mean writing a Python extension in C, which I have also had to do to get, because a vendor had a C library but not a Python library. So
you need to shell out to binaries. And
yeah, you can do some pretty ugly things. I don't really want to admit to having done some of them, but yeah, you kind of do what you need to do.
Great. Well, yeah, thank you, Joe and John.
All right.
Thanks, guys.
Thank you.
All right, next up, we have a couple of lightning talks, starting with Monica. Just a big green button advances.
Okay. Hello all, I'm Monica Dhok. I'm a PhD student in Indian Institute of Science, Bangalore, and I'm here to present one of my recent work on detecting loop inefficiencies automatically. This is a joint work with my advisor, Murali Krishna Ramanathan. Moving on, so software efficiency is very important. One cannot afford to lose customers because of performance issues in the program. But the problem is, performance issues are very hard to detect during testing, and therefore they escape testing and gets into production. Now, obviously, this is going to degrade application responsiveness and affect the user experience. So such kind of performance issues are termed as performance bugs in recent literature, and we will see how do you deal with such performance issues. So performance bugs are nothing but the implementation mistake that will not necessarily break your functionality, but it is going to affect the performance and therefore will affect the efficiency of the program. Now the problem is, these performance bugs are very difficult to catch during compiler optimizations as well, because compiler optimizations are generally in place and do not look at the program overall. So these performance bugs are really very crucial, and we need to fix them. Fixing them is going to give us large speedups and will improve the program efficiency as well. So let us start looking at these performance issues. There are various kinds of performance issues in the programs, especially in Java programs. There are memory issues, there are issues with garbage collections, and there can be issues with the caching techniques as well. So in this talk, our focus is on a certain specific kind of performance bugs, which are also termed as redundant traversal bugs. So let us try to understand what these bugs are before moving on. So redundant traversal bugs are defined as, so these exist when program iterates over a certain data structure again and again, when actually it is not being modified in the program. So to have a better understanding, let's have a look at simple example. So this is a code. There is a class A. It has a method called contains any. This method is taking two collections, C1 and C2 as input. And the method is iterating over collection C1 at line 2 and 3. And for every element that is traversed from collection C1, we are going to check if it is present in collection C2 at line number 4. So basically it checks if the element is present in C2. If it is present, it's just going to return true. If it is not present, it is going to return false. This is just some pseudocode that we are going to look at. Now the problem here is that if the contents operation at line number 4 is linear, the overall complexity of the contents any method is going to be quadratic. So the reason being there is outer loop which is iterating on C1, and for every element you are going to iterate on C2. Now how do you prevent this? The problem is if type of C2 is an array list, then this contents operation at line number 4 will be linear. Now we have to prevent this redundant traversal from happening in this program. So ideally the complexity of this program is quadratic in the size of C1 and C2. Now the way to improve this complexity would be to get rid of linear operation happening at line number 4. So what one can do is the collection C2 can be restricted to a type where the contents operation is not linear, rather it is constant time, and thereby we can get an improved efficiency, thereby improving the complexity. So basically, the ideal way to fix this program will be to typecast collection C2 to something like hash set, which has constant time contents operation, and then the complexity of the program is much better than quadratic. So now let's have a look at what happens. So this is a very basic model of testing technique. A developer develops a program. The program is shipped to a test engineer. Now it's test engineer's responsibility to write tests to check various functionalities in the program. And then these tests are generated and given to the bug detector. Now bug detector is going to look at the program execution and check if there are any issues like assertion violations, and then those are again passed back to the developer. Developer takes care of those issues, gives the modified version of the code to the test engineer, and then the cycle goes on. Now, the problem here is that in case of functionality bugs, bug detection is kind of better, kind of easier. So what I'm trying to say here is that if you have assertions in your program, and if you have tests written, then you can just whenever you come across an assertion violation, that essentially means that your program is not behaving as expected. And therefore, you have come across some issue which developer is supposed to take care of. Now, how do you detect bugs in performance? In the case of performance issues, you don't know that the performance issue is present unless you can give me a better version of the code which is running faster. Pretty straightforward, right? But how do you do it? So recently in the literature, there is a work called as Toddler, which is proposed in 2013, that basically takes a set of tests as input, analyzes its execution, and while it is executing, it will try to figure out if there is a repetitive execution happening in the program, as we saw in the earlier example. So this Toddler, it is going to take a set of tests and going to report if there are redundant traversal bugs in the program. Now, if you notice carefully, this Toddler is going to analyze the execution. Therefore, its tendency to detect repeated execution is completely based on the input set of tests. The set of tests should actually expose the program location, and also it should perform repetitive iteration at that particular program location. If that doesn't happen, Toddler is not going to detect any bugs in the program. So basically, the responsibility to write meaningful tests is on the test engineer, who is supposed to analyze the program, understand the semantics, and then ensure that the input test exposes such issues. Or rather, we need a technique that will automatically give you a set of tests which will expose such issues, highlighting the repetitive operations. So let us see what is the alternative option. So whatever we talked about so far was dynamic analysis, where we analyze the execution and we are completely relied on the test input. But now there are static analysis technique, which will just take a Java class as an input, go over the code, and try to figure out what possible performance issues can be present. There are such techniques, but they have multiple challenges. Now let us go over the challenges one by one. The first challenge is, given a bug, how do you confirm the validity of the bug? In case of functionality testing, you have an assertion failure in the program, which clearly gives you a proof that something is wrong with your program. But in case of a performance bug, how do you, what is the proof of its presence, right? Now, the second problem is, how do you expose the root cause? Now, given a bug, given a program location, when you are saying that there is a performance issue at this particular location, how do you fix it? What is the root cause of the bug, and why is it happening after all? Now, if you notice carefully, execution trace will be really helpful here for the developer to pinpoint what is the problem and thereby to fix it. Now, the third challenge is, how do you detect that the performance bug is fixed? Now, in case of functionality testing, developer fixes the program, and then when he runs the failing test once again, the assertion doesn't fail, and that basically means that the program is fixed to take care of that bug. But now when it is a performance issue, how do you know if it is fixed or not? So rather, if you have an execution trace, you can run it on the original version of the program P, which is going to take X minutes. Now you are going to run the same execution or same input on the modified version of the program, which should take time much less than X minutes. And that is what going to give you a proof that the performance bug is actually fixed. Now, this again motivates the problem of having a technique that will give you a set of tests to expose certain kind of performance issues. Now, let us have a look at what are the possible ways to fix the existing techniques. Now, you have Toddler, which is going to take a set of tests and analyze its execution. But can you fix it without having a technique that will generate directed set of tests? So there are multiple techniques like EvoSuite, Randup, JPF, CLE that you might have heard of. These techniques analyze program and they try to generate tests which achieve high coverage. So these are basically based, so Randup is basically a random test generator that is going to look at the various aspects of the program and going to give me a set of tests. Now you can ask me, why do you need a technique that is going to specifically generate tests focusing on performance issues? You can rather use these techniques which is giving me tests anyway. But the question once again is that we need very specific techniques for Toddler to be effective. We need them to expose performance issues in the program and ensure that the execution repeats certain kind of operation. So now, given the stage that we need some technique that is going to generate performance tests for us automatically, let us have a look at challenges involved in writing such performance tests. So to start with, so first challenge is virtual call resolution. As all of us know, real-world Java libraries use lot of inheritance, and at runtime there are multiple possibilities for a virtual call resolution. So what I'm trying to say here is that generating tests for all the possible resolutions of a method call is practically not possible. I'm just going to give out a test for every possible call resolution, and that is not what I want to do. My purpose here is to generate tests specifically for certain kind of issues without giving a huge set of such tests. So basically, I'm going to look at a particular call resolution only when I see that there is a problem with the code. The second challenge is that generating appropriate context. So even though a particular program location has a performance issue, we need to execute it. Our execution needs to be reachable there. And there might be multiple conditions that can affect the execution of that the program location with the issue. So basically, realizing the defect can be dependent on certain conditions that affect the reachability of the inefficient loop. So we need to take care of such conditions. The third one is, third one is arrangement of elements. Now the problem, so we figured out that there might be some collections that are being traversed again and again in the program. So you might say, why not just make sure that these input collections are huge and execute such methods? But that is not going to be good enough, because it's not just about populating the input collection with large number of elements, but what elements you are inserting into the collection, that also matters. So we proposed an approach called as glider. This is a scalable approach which will take a set of Java classes as input, and it is going to give me a set of tests in the output. So it is basically to generate tests for exposing loop inefficiencies. This is the underlying architecture for our approach. It basically takes Java library as an input, uses some random test generators that we discussed before, like JPF, CLE, Randup, and it is going to give me random tests. Now I will analyze this random test to figure out what are the program locations which might be having inefficient loops. Now with the help of this random test and Java libraries, I'm going to generate method summaries, which is the second phase of the approach. And this is going to flag every method with the potential information of loops, what are the methods being invoked, and what are the parameters being passed to these methods. Now in the third phase, once with the method summaries, I'm going to flag certain methods as inefficient methods, which will possibly have a potential inefficient loop, and some other methods like populator methods, which can be used in synthesizing a test that is going to expose this loop inefficiency. So with the help of all this information that is derived, in the last phase, that is test generation, we output a certain bunch of tests that is going to highlight the performance issues in the program. So, this is I'm not going to get into the discussion, the discussion of the design in detail because of time constraint, but our tool is available online. You can download it and run it with your Java classes. It's very simple to use. All you have to give it is a set of Java classes, and it is going to give you the bunch of tests exposing performance issues in your Java classes. Okay, so I just wanted to show you one of the performance bug that we caught. So this is a JFree chart library that basically displays quality charts in your applications. Many applications use this library, and when we gave this library as an input to Glider, it detected a bug for us, which was basically the redundant traversal bug. We reported this bug to the developers. They acknowledged the presence of the bug and has incorporated the changes that we have suggested. This was really important because if your application is using this library, the application is going to incur a huge slowdown. So after the performance fixes that we suggested, there was a 314x speed up for this program. Okay, so overall, just wanted to highlight the results. So we have implemented our approach on Suit bytecode framework, which is basically a program analysis tool. We evaluated our implementation on 7 real-world Java libraries, and we detected 46 bugs, and out of which 34 bugs were previously unknown. We have reported some of these bugs to the Java developers, and they have most of the bugs have been acknowledged by Java developers. Lastly, we figured out that this test generated using Glider significantly outperformed the randomly generated tests. That's all. I'm ready to take any questions. Thank you.
Excellent. Thanks, Monica. I can't wait to run this on some of the Java classes I've seen. Yes, we had one that you already answered. I think we only have time for one question since we're lightning talks, but micro benchmarks are notoriously difficult to get right, e.g. due to JIT. How does Toddler ensure it measures real-world performance?
So right now we are just looking at simple, we are looking at the Java classes. We have not considered JIT kind of stuff, but yeah, I think I'm ready to take it offline and discuss more on it.
Okay. Well, thank you.
Okay.
Very good. Excellent talk. All right, keeping on schedule with lightning talks. Next, we have Emmanuel.
Yep. The clicker, this one? Okay. Hi, so I'm the last one standing between you and the lunch. So as you all know, in Google, there's a value of food a lot, so I'm going to try and be as quick as possible. So 3 hours to 3 minutes. I usually give this presentation for about 40 minutes, and now I have to eat my own dog food and do it for about 10, 12. So let's start. So what is this all about? We had a bunch of API tests, and we used to run them every night. It took 3 hours to run them, and now they run for 3 minutes. So this is the actual scale, 60 times faster. This white dot for you guys at the back, this is 3 again. So that's the actual scale. So how did we do that? So now it comes before and after slide, like those infomercials. So this is the actual screenshot of the Jenkins. As you can see, 3 hours. The last run here was 4 hours and 40 minutes. And we used to run them every night. And what would happen in the morning? We usually, we're gonna have to play whack-a-mole, find the developers responsible for the breakage. And it was hard because you go to the first developer and what did you do yesterday? He would say, I don't remember, I got drunk last night, don't ask me, ask the other guy. You go to the other guy, he said, I fell in love with this girl, I don't know, I don't remember. So it was really tough. So we said, okay, enough of this bullshit. So we set a goal, let's run all of that for 3 minutes. So why 3 minutes? Basically, the idea was to give comprehensive feedback after every code change to the developers. And after every code change, you run all the tests that you have. No more smoke tests, no more nightly runs, and so forth. So this is the situation now. So 2 minutes, this is a little bit more than 3 minutes. You want to see some numbers today, and the numbers are not going to be meaningful to you. They mean to us, but not to you. And you're going to see some techniques that are not brand new. There is no magic fairy dust, but it's all about continuous improvement. This is what we all have in common. All of us are unique snowflakes, unique challenges in our companies. But if you set up a goal and take small incremental steps to achieve this goal, put the time and the effort, you will achieve some amazing results. So this is our journey. So the first thing that we did is dedicated environment. All the tests were running on environment that was shared with the developers that were used to put their code together before pushing it on production. We didn't have a dedicated environment. So the first thing that we did is run everything in dedicated environment only for automated tests. So this is how we start 180 minutes. By having a dedicated environment, we were down to about an hour of the execution time. So the next thing that we had to do is databases. We were still using the shared database because it contained a lot of data useful for those tests. This database was heavily used by bad jobs and some other stuff that happened during the night. So we figured out if we wanted to really fast test, we need to have a separated database. But this was a problem because we had to rework most of our tests to insert the data that they need. So we had to re-engineer the framework. It might sound a little bit crazy, but this is what happens right now before every test case. So we call a bunch of APIs, and we manually, if we don't have access to the APIs, we manually change something in the databases or add some rows just to set up the playing field, just to do the setup, and then the real test case starts. Before that, it's only setup, but. Being able to do that means that now we can run the tests on empty database, on full, on dirty, on integration, on stage. We don't run those in production because it's a little bit risky, but you get the idea. Basically, we are free to use every database. So we've saved about 30 minutes with that. So next thing, external dependencies. What we do is software as a service. We collect a lot of data from the biggest social networks, and even sorry, Google Plus is also there. Sorry, someone from Google Plus team. Okay, so the idea was that all of the test cases had in one way or another connecting to external service. And if this service was down, say Twitter was down and the test case were failing, and this didn't have anything to do with the developer pushing the new code. So we wanted to basically stub, fake, simulate, pick whatever you like, those with something that we control, so that now I believe Google calls these hermetic servers, like you don't have access to the outside world. Everything is wrapped up and doesn't leave your network. So this is I don't know if you see the font. This is the landscape as of sprint of this year. A bunch of open source tools, WireMock, SoapUI, mock server. Stub4j that we evaluated, but we had some specific requirements, like being able to act as a transparent SSL proxy, basically. We wanted to monitor all the connections and figure out which we want to fake and which we want to pass to the real service. I want to be able to return some real binary data, have some local storage, dynamic responses, etc. And none of those would fit the bill. So we didn't want to do it, but we had to develop our own tool to basically scratch our own itch. It's called Project Nagwell. It's going to be open source really soon. We're waiting for some external stuff to happen. It's really cool, and you'll be able to check it out, I think, in a month or so. So by stubbing all the external dependencies, faking HTTP traffic, we didn't gain much in terms of speed, but we gained a lot in terms of stable tests for non-flaky tests. For us, the biggest reason for flaky tests was the external services, and sometimes the internet is down or is slow, but now we control everything. So moving to containers, we didn't want to do that initially, but we had this big monolithic application, and developers decided that it's a wise idea to start splitting this whole big monolith to smaller services. And we basically had to follow suit. But we didn't have enough servers to mimic what the production environment looks like, so we had to use containers. And we used Docker, so what we did was create one service, one container. And when we run all the tests, we were actually in a big surprise. The execution time grew. And we started scratching our heads, and you see I did a lot of scratching. Until we figured out what the problem was, we use Docker. So as you know, it uses layered file system, and it's really bad if you have high disk I/O operations. So we measured that for our case, it was about 3 times as slow the I/O performance than using a real file system. So our biggest user of file system I/O was the databases. So we figured out, okay, let's run the databases in memory, so to see how did we go, because we don't need the data, it's only fake data, we run everything in memory. Now, so we go back to where we started, basically, but at least it didn't get worse. So next, don't remove this test data. What we used to have a logic in the framework, back when we were using the shared testing environment, each test case would create the data, and then at the end it would delete the test data so that we don't pollute the whole environment when we do manual tests. But now we did not need that anymore because we have dedicated environment. And the thing is, when you stop the container, just the data evaporates. So there is no need for this heavy logic to do that kind of search and deletion. So we were down to about 4 or 6 minutes, and it's not much, but every little bit helps when you're up in that point. So the next thing that we did was the obvious thing that usually everyone starts with, so run stuff in parallel. But according to our experience, this should be one of the last things that you do, run stuff in parallel. When you run them in parallel and you get variation in execution time, so you don't know if it's a normal variation or it's something caused by you trying to improve the system. So try to expand all your other options and then try to run in parallel. That's the actual graph of the threads that we run tests in and the execution time each one took. As you can see, it's easy to see the optimal value is 10 threads for this. This is per hardware specific, so if we add more memory and CPU, it may shift to the right. But we run those in 10 threads, and so the execution time was about 5 minutes. Still a little bit off our initial goal of 3 minutes, so we had to do something else. And it turned out, equalizing workload, it turned out that the software that we used to run all the tests, the driver, it did not do a good job to separate the test cases equally into each thread. So as you can see, thread number 3 had about 130 test cases in it. And so everyone had to wait for thread number 3 while the other were idle. So we had to manually reduce the workload. So this is the picture after. And it's not perfect, but it did the job. So we were down to about 3 minutes. So this is how the whole picture looks like. The actual results were even a little bit better. So that's a screenshot, and they took 2 minutes and 15 seconds. But this doesn't make for a good presentation title. It's mouthful, 3 hours to 2 minutes and 15 seconds. So stick to 3 hours to 3 minutes. And at this point, we have exhausted our options to optimize via the software. So our only option was now to go after the hardware. So a couple of months ago, we upgraded basically mostly the RAM and the CPU, the machine that we run, and now the tests run for 1 minute and 38 seconds without doing anything else. This runs on single machine, on single server. If we want to go below the 1 minute mark, and this is right now what we're doing, it's super easy right now to scale horizontally. And so this is our current option. This is what we're going to do. We're aiming for sub 1 minute execution time. For comparison, our unit tests run for about 45 seconds, about 3,000 of them. But they don't touch the database, the network, and the file system. Those guys do. When you have high-level tests, these are most of the complaints that you get. Compared to unit tests, everything else is slow. So we accidentally addressed all the issues that we had with high API and UI level tests. So they're not slow now. They run for 3 minutes, and we're aiming for less than 1 minute. They're not unreliable. Like I said, we control all the dependencies, and no one else uses those machines, so they're only dedicated for fast tests. The entropy is lower. This is a little bit harder. Cannot pinpoint the problem exactly. Sometimes when your test fail, high-level test, you get internal server error, and you don't know. You're lucky if you get a stack trace. Most of the times you just get internal error. Something happens somewhere, so it's really hard to figure out exactly what. But having so much faster tests actually changed the behavior of the developers. Now they start to getting used to this fast feedback, and before they used to push their code once a week, from once a week to 2-3 days a week to once a day to every hour. And when they push 3 lines of code and the test fail, then it's pretty obvious which of the 3 lines is a problematic one. So by having super cheap and fast, reliable tests to run, so we actually run everything on every commit. Like we run static code analysis, we run linters, we run custom tools, unit tests, and those tests. So there's nothing else to run after each commit. We are able to push on production or continue to manually test if we like. And those are no longer problems for us. What we think is that in the future, this is what we should aim for, to be able to run all of your tests, not only the unit tests, but everything for no more than 3 minutes. We think that this is going to become a standard development practice, the way right now we put all our code in version control system and we use CI. So this, a couple of years ago, this was, I consider a crazy practice. But what you want to do is keep developers in the flow. What happens if you have a pipeline that it takes 15, 20 minutes to run all your tests? So developer pushes their code, and what happens is while they're waiting, they go to check their Google Plus, said no one ever. Facebook page. They go to make a coffee, make a sandwich. They check their, Tinder app, Grindr, whatever your thing is. And when they come back, 15, 20 minutes later, they have forgotten all of that stuff. Build failed. What did I do? The idea is to keep everyone in the flow. Okay, so keep them in the flow. That's my last slide. 2 books to help you with your journey. The first is the Go by Eliyahu Goldratt. Introduces a theory of constraints. So basically, you have one big bottleneck. You work on this bottleneck. Then you have additional bottlenecks, but they are not visible until you fix the bigger bottleneck. It's basically reads as a business novel. The next one is Toyota Kata by Mike Roder. Introduces a continuous improvement kata. So you set up a goal and you take the small PDCA cycles by Dr. Deming, plan, do, check, act, and you take every day, you take small steps, and when you hit a problem, take a step back, the way we did with the containers. So that's all I had to say. Thank you.
Excellent, thanks, Emmanuel. And I thought my comments on JavaScript were harsh. Google Plus burn, ouch.
I hope they didn't do a parking lot therapy, the Google Plus.
I think you're okay. We probably have time for one question. How do you ensure your API stubs stay current if and when the stubbed API changes?
Yeah, that's a very common question. So, so the three things. The first thing is that we deal say Facebook or Twitter APIs, and they announce a new version, and we initially don't switch first to this version. We switch only internally to using the, say, version 2.8. And if we detect some problems with the stubs, we adjust the stubs. We have time to do that. And when we are all set up and we think we're ready in testing, then we push to production. Then we use two other things. We also do extensive monitoring. So if we monitor some problems, we adjust the stubs. We also, the third thing that we do is we do a lot of contract tests. We basically ping Facebook or Twitter or Google Plus for is this the JSON that we expect to be? So every 10 minutes or less, we do those kinds of tests. And we did not used to do those kind of tests, but what happens is that Facebook at one point changed a little bit in their JSON responses. They added additional field just for one day, and it caused us thousands of dollars of losses for us because we didn't handle this case. So we learned our lesson, and we use contract tests to check if what they return is really what they said they would return.
All right, very good. Another round of applause.
Yeah, so thank you.
All right, we are on for lunch right now. Today we have an hour and a half for lunch, so you can leisurely take your time. The groups heading to the big cafeteria in TC4 and TC1 will meet outside. Anybody who wants to go to Cornerstone right here in this building, stay in the room here, and we'll lead a group over there. And we'll be back at 2:30.
Test, test. Hey, hey. Mic check, check, 2, 2. Hey, hey. Hey, hey, check, check, 2, 2. Hey, hey. Hey, hey, mic check. Hey, hey, mic check, 1, 2, 2, 2. Hey, hey. Oops. Hey, hey, mic check, 1, 2, 2, 2. Hey, hey, mic check, 1, 2, 2, 2. Hey, hey, 3, 4. Mic check, 1, 2. Hey, hey, mic check. All right, hey, hey, thank you. Check, 1, 2. Hey, hey, mic check. Hey, hey. Sounds okay. Hey, 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 hey. Well, we have to figure out.
clicker, and it's Raul. Yeah. Make sure I get it right. Every direction. All right, welcome back from lunch. I hope everybody had a nice leisurely hour-and-a-half lunch, and you were able to discuss some of the topics that have come up so far in the conference. How was it today? Good? Good food? All right. For everybody on the live stream, everybody nodded in agreement with what I was asking. All right. So now we're going to get back into lightning talks. First up, we have Rahul from Oregon State University.
Okay. Hi. I'm Rahul Gopinath, a PhD student from Oregon State University, and this is a summary of my research along with that of Iftikhar Ahmed from the same university. So this talk is about evaluating test suites and the best metrics we have in actually ascertaining the quality of our test suites. And by quality, I mean the ability of a test suite to find bugs. So before starting, a question. So how many of you were present at GTAC 15? Okay. So in that talk, there was another talk with a very similar title that said that code coverage is not a strong predictor for test suite quality. So this is actually a counter argument. So it was suggested previously that we should not actually look at code coverage, and it's not trustworthy, and we should look at something called mutation coverage. So I hope to convince you otherwise, and I also hope to show that the suggested gold standard, that's a mutation and a mutation score for a test suite, is not only expensive to actually compute, but also inconsistent, and is very much dependent on the tool that we use to measure the mutation score. So essentially, mutation score is not really a silver bullet, and we have to use it in conjunction with the coverage of a test suite. So, well, when is a program ready to ship? Notwithstanding the comments about testing it in production for the Google Drive, the Google Automatic Car, this is one of the biggest decisions that we as testers have to make. And in the old-fashioned way, we usually stop testing when we are reasonably sure that the bugs are completely over. Not the new way, of course. So that means that an effective test suite is very important, and that's what we really need to find. How do we actually make sure that our test suites are effective? And how do we actually evaluate this test suite effectiveness? Of course, there are two main things that we all know that we can evaluate in a test suite. How good is its coverage of the program elements? And secondly, what is the strength of its oracles? By oracles, I mean just assertions, because if you don't have assertions, then it's useless. So in the previous GTAC, Laura Inozum et al., who actually did that talk, she suggested that coverage should not be relied on because it rarely provides more information than just the pure size of the test suite. So she instead suggested mutation score, where the effectiveness of a test suite against a set of mutants is evaluated. How many of you actually know mutation score? How do we evaluate mutation? Okay, so at least I know that there are a few people who are around here, and I also heard first day that Google is also, some of the people in Google are also using mutation score, so it's not completely out of the blue. The unfortunate thing is that, well, as a basic idea, what we do in mutation analysis is that we start with a program, and then for each token in the program, we start introducing changes. What are the changes that are valid grammatically that if you compile will not result in an error? So we have a large number of variants to that program. Each variant you compile and run it against your test suite and see how many of these variants are actually caught by the test suite. The total number of variants that are caught by the test suite divided by the total number of mutants gives you the mutation score. That essentially means that this is the actual effectiveness of the test suite. The unfortunate thing is that after Laura's speech, programs, especially in the programmers community like Hacker News or Reddit, they all took it to mean that we should really completely discard coverage. And the comments were that coverage is meaningless in the real world, and arbitrary lines in sand, such as 90% or 100% coverage, is pretty much, they don't provide any utility. But is that sufficient? I mean, is it sufficient to ignore coverage? So that is what we set out to find. So to start from the very basics, there are two factors, of course, assertions and coverage. And coverage on its own is useless without assertions, and assertions have to be paired with good high coverage test suites. And Laura's idea is that coverage is completely determined by the size of the test suite, and that it doesn't actually tell us anything new because it so closely correlates with the size of the test suite. So since test suite is so easily determinable without even actually running it, what is the point of actually looking at coverage? And why not just use the test suite size instead? That was the point in the previous talk. However, the question is, does it actually make sense to control for the size of the test suite? It's not a good measure. We do not actually know what is the maximum number of tests that can be there in a test suite, even for the same program, because you can have different test suites for the same program. And different tests are not necessarily equivalent in strength. There can be some tests which actually identify a larger number of problems, and there might be tests which are specific. So size of the test suite, while it is simple, is not really a reasonable measure because we don't really have any endpoints. There is no 0% test suite size or 100% test suite size. So one of my points is that even if coverage just measures test suite size, it's a good thing to have because at least it tells us how large the test suite is. And secondly, none of us actually cares about the total number of tests that we run. We may have a time budget, we may have other kinds of budget, but not really related to the number of tests. So for a practicing tester, there is only one single question. Can I use coverage to measure the test suite effectiveness? And this is what we set out to find in my research. So what we did was that we started with 250 real-world programs for the study from GitHub. And the largest was greater than 100 kilolines of code. So these are not toy programs. And we checked coverage for both organic, that is coverage, the test suites that are written by people like us, and also machine-generated tests that are generated by random. So we found that for these organic test suites that are written by human beings, if a statement is covered, then that statement has 87% chance of, if there is any mutant in that particular statement, that mutant has 87% chance of being detected. And if you have statement coverage, then that can actually predict mutation score with 94% certainty. That is, once you control for statement coverage, mutation score actually provides only 6% extra variability that you can evaluate. So this is another thing. The previous blue ones were developer written, and these red ones are automatically generated by random. So as you can expect, the oracles are really bad, and there is only 61% chance that if a line is covered, any mutant in that particular line will be caught by the test suite, by the randomly generated test suite. So given this result, there's a question that we can ask. So if coverage is so highly correlated with mutation score, what's the point of using mutation score? I mean, we can essentially just use coverage and predict the mutation score instead. So until now, we assume that coverage provides no extra information with respect to test suite size. That is the assumption that Laura started with. That was the result that Laura had. However, the question is that particular question, is that assumption really true? Remember that her results were actually from just 5 programs, even though very large programs, but still only 5 programs, while we actually have 250 programs. And she was also using random subsets of the same test suite again and again and again. So is it possible that her conclusion that coverage is directly related with test suite size may not actually generalize to the larger programs? So this is what we actually wanted to find. So what we did was that we eliminated the effect of test suite size statistically, and we actually found that even if you control for the test suite size, for the remaining amount of information that is provided by the mutation coverage, 74% of it is still explained by the statement coverage score. So that means that the previous assumption or previous result of LoRa from these 5 programs are actually not generalizable to a larger number of programs, especially large programs and more random programs, not exactly chosen by the researcher themselves, which is a major issue in the software engineering research, because usually there is a problem that we rely very heavily on specific programs which are used again and again. So even if coverage is a reasonably good criteria, it's still possible that we might actually go for mutation analysis, because in some sense, mutation analysis comes very close to actual bugs, because we are actually introducing bugs into the program and evaluating how many of these are caught. So should we actually use mutation analysis? Is it actually ready for the prime time? Or the question is, should we use mutation analysis as the primary means of evaluating quality of a test suite? So unfortunately, mutation analysis is beset with a large number of problems. The biggest thing is, of course, the large number of variants. Each of these variants have to be tested by the complete test suite. And there is no way out of it. We essentially have to evaluate each of them. Even small little programs like B²-4AC tend to produce large number of mutants. And secondly, so that mutation score is really costly. And even if you ignore the size of the mutation analysis, there is another major problem. These are called equivalent mutants. The problem is that these changes that we introduce, the tiny little changes that we make to the program, they need not always result in a fault. Some of them can actually result in programs which are behaviorally same as that of the original program. These are called semantic clones. Or in terms of mutation analysis terminology, these are called equivalent mutants. The problem is that if you have a program which produces, say, 50% equivalent mutants, none of the test suites that you can ever write is going to have a mutation score that is larger than 50%. So, and unfortunately, there is no general way, as of now, in software engineering research, to identify how much of mutants would actually be equivalent given a program, nor can we identify, given 2 programs, whether a mutant and a program, whether the mutant is going to be equivalent to the program. So this is a result from Turing computation. This is called Rice theorem that essentially says that a general way to do that is pretty much impossible. So that means that a low mutation score is not generally indicative. It doesn't actually indicate a low quality of test suite in general. I mean, it can be true for most of the times, but if your program is a unique snowflake, then it is possible that you have a low mutation score, but you actually have a test suite that is highly effective. And even worse is something called redundant mutants. So redundant mutants are still semantic clones. They are semantic clones of each other. They have a fault in them, but there are a large number of mutants which are exactly the same fault. So if your test case detects at least one of them, then the rest of it falls. So what that means is that if you have a large amount of redundant mutants and your test suite catches one of them, then you will have a high mutation score, even though the test suite may not actually have been very effective. So we can't really trust mutation score on that score either. And finally, this is a problem with the current state of the art. This is not a problem with mutation analysis itself. The problem is that different mutation tools have very different, they act on very different levels. So you can have a mutation score mutation tool that acts on the assembly or in the machine code or on the source code itself. So here I show 2 different ways in which you can have mutants, one on the source code itself and the other on the assembly. And the problem is that we have on the left the mutation score that is computed by 3 different tools that act on 3 different levels. And the problem is that these tools do not actually agree with each other that well. So you can see that there. So this is the current state of the art for mutation analysis. So it's not consistent across different tools. So finally, the proof of coverage is actually, the proof of it is in the pudding. So if coverage is a good measure of test suite effectiveness, then a well-tested program that we assume by using coverage should actually result in fewer bug fixes. And we should be able to find that difference between covered and uncovered programs, or covered and uncovered lines in the same program. And this is what we did next using the same 250 programs. So what we did was that we started with an epoch and then counted the bug fixes that happened on that particular line until it was actually wiped out by a feature fix. So what we actually found is very interesting. We found that if there is a line that is covered, and you compared that to any general line that is not covered, a covered line is, or an uncovered line is twice as likely to have a bug fix as that of a covered line. And that is true across statement, block, or method level. That is, if you have a method that is at least tested or covered by some test case wherever, that method would have half bug fixes in its future compared to a method that did not even have a single test case covering it. We don't have sufficient data for class, so you can see that our p-values are somewhat low. I mean, we don't have significance there. So yes, coverage is a very strong defense against future bugs, irrespective of what others say. So in summary, coverage is still the best measure that we have for evaluating test suite quality. And mutation score can at best provide a secondary measure, so don't rely solely on mutation score. And also, if you're using mutation score, understand the problems of mutation score. It is expensive, it is costly, it is unreliable, and provides maybe a little extra information, like 6% beyond coverage. And more importantly, in addition to the the simple measures like mutation score or coverage, if you actually look at which statements are actually not covered and try and see why it is not covered, or look at even mutants, look at the mutants that are not killed and see why it is not killed, that is probably a very good testing technique in itself. Yeah, thank you.
Excellent, thank you, Raul. So with Lightning Talk, we'll take one question. Oh, wait. It's Laura from last year. She's calling. She wants a word. She wants to talk to you. No, just kidding. So I think that covers the first one. We'll ask, do you have an opinion or studies on code coverage effectiveness with property-based tests?
So I will start with the first one first, because this is an ongoing argument between us, whether mutation analysis is ready for prime time use. And you know what my opinion is. So software engineering community is trying to come up with better tools to actually remove equal mutants and redundant mutants and come up with better tools. So that is where engineering community as of now stands. Okay, and do you have an opinion on studies on code convergence effect? Do you mean code coverage? Well, code coverage effectiveness is pretty good. And I think property-based tests are really good, especially things like quick check. Those actually help you quite well. But the problem with property-based testing is that it's really hard to write that kind of tests. I mean, you really need programmers who are well-versed in that. Yeah.
All right, excellent. So thank you, Raul. All right, so next lightning talk up, we have Taejun and Joseph.
Hi, I'm TJ. This is Joey. We are software engineers on the productivity engineering team at Box. And to those of you who aren't familiar with what the productivity team does, we own all the tooling and services relating to continuous integration, development, and testing. So think of tools such as Git, Jenkins, test infrastructure, and a service called Cluster Runner, which is a tool that we built in-house at Box a few years ago and open sourced. And it's the topic of our talk today. So Cluster Runner is a distributed service that we built to achieve a single goal, and that's to execute tests in the fastest way possible. And it achieves this by horizontally distributing a workload across whatever computing resources that you allocate Cluster Runner. And Cluster Runner efficiently utilizes these resources by using historical timing data from previous builds in order to best distribute the workload. You interact with Cluster Runner through a RESTful API that we provide, and this lets you integrate Cluster Runner with any automation or CI that you might already have. Now, I could talk all day about all the features of Cluster Runner and why it's so great, but showing is better than telling. And so we've dedicated the second half of our talk into showcasing Cluster Runner in action. So I'll be deferring the list of all the features until then. Now, this being the test automation conference, I don't need to sell you on the importance of writing and running automated tests. We're all here because we care deeply about shipping quality software in a timely manner, and we want to explore the various aspects of achieving that. So the aspect we're focusing on today with Cluster Runner is test volume, specifically running the most amount of tests in the shortest amount of time possible. Now, test volume, when you first start writing unit tests, is not really an issue, because there's few enough of them, and they run very quickly, and your developers have no issue running them locally on their dev machines. And eventually, you will probably adopt a CI system, such as Jenkins, to run them remotely and asynchronously on a more powerful machine than your MacBook, probably. But as time goes on and your code base grows, your test code base should also grow, because your developers should be writing unit tests, hopefully. And that leads to the development and test iteration loop getting longer and longer, which in turn turns into engineers losing productivity, waiting for their automated test suites to complete. And we saw this happen firsthand at Box. So we introduced developer-written integration and unit tests in 2012 to our primary code base, which is written in PHP. So we use PHP in it. So a couple weeks in, our entire test suite took about 10 minutes to run on a single machine serially. And a couple months later, we're up to 45 minutes for a single build. A year later, we're up to 3 hours. And today, we're up to 30 hours to run our PHP and test suite once on a single machine serially. So this is what success looks like. You want a lot of code coverage. You want to instill a culture of quality and testing in your engineers. And getting to this point is very difficult, and it merits a talk on its own. But today's talk is it's not about evangelizing good testing practices. It's about what do you do once you reach this point? Because you obviously can't expect your developers to wait 30 hours for a build to complete. That's absurd. And this is not a build that we want to run once per release. It's a build that we want to run every single time a developer pushes a code review, merges a trunk, has some sort of experimental changes that they have in some remote branch. So at Box, that roughly translates into several hundred builds every day. So the target here is to run this 30-hour test suite several hundred times every single day. So what do you do? Well, it seems like a problem that you can throw money at in the form of test hardware to parallelize the test execution. So test servers are relatively inexpensive compared to the salaries of engineers, especially in Silicon Valley. So it's an obvious investment to make, and it's one that most companies do make. So let's say you got the purchase order approved. Let's say you ordered and delivered the servers. Your data center guys have networked and racked these servers. Now, all you need is the actual software to parallelize the execution of the tests to utilize this new hardware capacity. So before we determined what tool to adopt to do that, we first had to analyze what our requirements were. So at Box, we got several teams, got dozens of Git repos written in several different languages, and they have their own corresponding unit testing frameworks. And additionally, we have functional tests, performance tests, linters, and all that good stuff. And as I mentioned in some of the previous slides, some of these test suites take a very long time to complete. So based on these facts of life at Box, we devised a set of requirements for the tool that we want to adopt to parallelize our tests. So first requirement is that it has to be easy to configure and use. The engineering teams at Box own their own CI system and the configurations of their tests. So if the tool requires like an entire DevOps team to configure and use, they will simply not adopt it. Second requirement is because we have so many different code bases and test technologies and frameworks used, it has to be test technology agnostic, because we don't want to use a tool that works just for one team. It's got to work for everyone. And last but not least, it has to give us fast test feedback. And the whole reason why we're investigating this is to get fast test feedback, so that's an obvious requirement. So at this point, we did what any responsible engineering team would do. We looked online for existing solutions. Ideally something open source, but we were willing to pay for an enterprise license if we found something that we liked. And at the time when we searched, we didn't find anything that met all of our requirements, which is very surprising to us because it felt like it should have been a solved problem by now. And so we decided then to solve the problem once and for all, and we invested a couple quarters into building Cluster Runner, and we made it publicly available in 2014 by open sourcing it. So we've been using Cluster Runner since 2014, and it's an absolutely irreplaceable service in our CI stack now. The 30-hour test suite I was mentioning earlier runs today in 17 minutes. 17 minutes. So to get you an idea of the order of magnitude of the difference, 30 hours is more time than I spend writing code on a very good week. 17 minutes is how long I spend replying to an email. So the only reason why it takes 17 minutes to complete is because our longest test file in our PHP test suite takes about 16 or 17 minutes to run. So if someone were to break up that test file into smaller test files, Cluster Runner would give you feedback in as fast as the next slowest test in the test suite. All right, that's enough context. I'm going to hand it over to Joey to show you guys Cluster Runner in action.
Thanks, TJ. All right. Go. Okay. So I'll go through the 4 main steps that you would follow to set up Cluster Runner up for your project. So the first one being bringing up the cluster, so getting the Cluster Runner service running on your infrastructure. The next part, setting up your project, so basically just adding a config file to your repo. And then after you have your cluster set up and set up your project, obviously you want to execute your build and look at the results. So first, bringing up your cluster. Cluster Runner, it's all contained within a single executable. So we have the master service and the slave service, all part of the Cluster Runner executable. So this is pretty straightforward. There's no extra dependencies. You just run Cluster Runner master, you give it a port, and then you run Cluster Runner slave on all the slave hosts that you want to attach to the master, and basically just point it at the master. All right, and this can be done manually. This can be done by your by some config management tool. This is just how you would do it manually. Cool. So that's it for setting it up. That's once it's up and running, you can hit an endpoint on Cluster Runner's API. So Cluster Runner communicates via REST APIs. This one is the slave endpoint. So just taking a look at what that would look like. So this has 2 connected slaves to it, and this just gives you a whole bunch of info on each slave. So basically, its current status, so if it's working on a build or not, and then some kind of state information, like how many executors it has, and that type of thing. Cool. So that's it for setting up the cluster. It's pretty straightforward. So setting up the project. So as I mentioned, you will just add a single Cluster Runner YAML file at the root of your project repo. This is a small file. I'll show you an example here in a second. It tells Cluster Runner which commands you want to run your tests, and also how to distribute them across the infrastructure. So yeah, here's a very simple example of Cluster Runner YAML. So you can define multiple jobs in a single Cluster Runner YAML file. This just has one job named PHP unit. And the first section, commands, tells Cluster Runner how to run your tests. So in this example, we're just running PHP unit on each test file. The second section describes how to distribute your test across the infrastructure. So a single unit of work in Cluster Runner is called an atom. And this atomizers command tells Cluster Runner how to generate those atoms. In this case, every atom corresponds to a single test file. So we're just running a find command, giving it star test.php. This will just return us a list of all the test files, and those will be plugged into that command section up above. We made this very simple intentionally. This was like one of our main requirements when designing Cluster Runner. As TJ mentioned, we're a central team at Box. So we own the cluster and the infrastructure that it runs on. All the individual teams own these files in their projects. So the individual teams own their tests. They decide what goes into the Cluster Runner YAML file. So this makes it really easy to separate ownership. Cool, so this is like an example of the individual commands that would be generated after we combine those 2 sections together. So we're just running PHP unit on each test file in the repo. All right, and then, so each of these commands basically gets distributed across the infrastructure. So now we're ready to execute a build. So this is another subcommand of Cluster Runner build. This works like an API client of the Cluster Runner master. Basically, all it does is send an API request to the master. You could easily just do that API request manually. So this is pretty straightforward. You just give it where the master host is. You say it's a Git type project. Give it the URL to your Git repo, and say which job name within your Cluster Runner YAML that you want to run. All right, and that's it for running the build. So if we could play the first video. This is a visualization that we built to kind of visualize how a build runs. So the big circle represents a build. The small dots represent the slave hosts. So you'll see that one popped off right away. So that means all the work is in progress. That slave couldn't pull any more work for this build. And then Obviously, there's a few tests that take a lot longer than those first tests, so these second hosts will take a lot longer. And it's done. Okay, we can switch back to the slides. Cool. So the build ran, great. Now we actually need to look at the results to get anything out of it. So here's another endpoint on Cluster Runner, the build endpoint, just the build ID. So you look at this, it'll give you a ton of information about what happened during the build. So just kind of starting from the top, you can see the status is that it's finished. There were no failures. It gives you a human-readable details message. 5 of 5 subjobs are complete. An error message if there was any, number of atoms, et cetera. The term subjobs, basically Cluster Runner batches, this is kind of an aside, Cluster Runner batches atoms into subjobs to send them to the slave hosts. It just does that to reduce network overhead in sending tons of atoms to the slaves. So that's what subjobs means. Another nice thing about this is this will list all the failures right here if there were any. Luckily in this case there were not. Cool. You can drill down even further with the API, so you can look at each individual subjob that ran. Looking at this, it's kind of small. Hopefully you can read it. Basically, it will list every atom that ran, which command it ran, and the amount of time it took, the amount of expected time it took. So as TJ mentioned, Cluster Runner is keeping track of how long each test takes to run and using that information in future runs. Cool. And you can also get the exit code from here. So Cluster Runner uses the exit code to determine failure or success. The last way that you can get build results is you can actually download an archive file containing all of the build results. So this is pretty similar to the last two API responses I showed. If you download this file and expand it, you get kind of a breakdown of each subjob or atom that ran, and then you get the command, the console output for that test run. So this would be like the console output from running PHP unit, exit code, and amount of time. Cluster Runner also lets you, in your Cluster Runner YAML, put files into an artifact directory. So if you did that to save artifacts from the build, they would be in this archive file as well. Okay, so here's kind of the different picture of the same build that I showed, the same animation I showed. You can see that one slave host finished very quickly. There were 2 other ones that went on for a little longer. And maybe one of the first things you notice is that this is not the best way to run these. This is not the best order to run these in to take advantage of your whole infrastructure. So Cluster Runner it'll look like this the first time you run a build. The next time you run it, it will optimize. So it'll use that timing data from the previous run. It'll run the longest test first, and generally you get way better timing for future runs. Cool. So here's a quick video that we took a while ago. This is our production Cluster Runner instance at Box. So it's sped up, but you can kind of get an idea of how dynamic this is, and you can see slave hosts switching from one build to another. They don't have to wait for all the slave hosts for a single build to finish before they can work on another build. Yeah, so that's it. We can switch back to the slides. We don't have to wait. Thank you. Cool, so that's pretty much it for setting up Cluster Runner and running your build. This is kind of our wish list, what's next, what we want to do next. AWS integration with auto-scaling. So right now, Cluster Runner has endpoints for adding slaves and removing slaves pretty easily. It'd be cool if we could do that dynamically and scale up the fleet as we needed it. Also Docker support, so running tests in containers. Just to avoid environment differences, improvements to the deployment mechanism, in-place upgrades so that you don't have to take the whole cluster down to update it, and then a web UI. So the visualizations I showed are kind of just individual dashboards right now, so it'd be cool if we could integrate those and actually have a full web UI. So yeah, we love it when people get involved. We love feedback. If you want to check out more, go to clusterrunner.com, and that also has a link to our GitHub repo. And if you have any questions, email us at productivity@box, and we will be happy to help you. And that's it. Oops.
Very good. Thank you, Tejan and Joseph. Although I think if you had built that cute visualizer first, people wouldn't have minded waiting 30 hours just watching that.
That's probably true. It's very
saved a lot of time.
People always just stare at the TV near our area. Yeah.
Who wouldn't want to watch that for 30 hours? We have time for one question because of the lightning talk, but how do you distribute the binary to the testing nodes?
Do you want to take this one?
So yeah, this is a part of our deployment mechanism. So cluster ships with a pretty simple command line tool, and a part of it is cluster deploy, and you specify a list of slave hosts. So the master takes its own copy of this binary and deploys it to those slaves. So there's a prerequisite requirement right now where the masters and the slaves have to have SSH keys exchanged beforehand, otherwise the deployment will fail. So the short answer is the binary ships with both the master and the slave in the same binary, so you can run it in different modes.
That's part of the deployment thing that we want to improve.
Yeah, that's something we're not happy with that. We'd like to deploy it as an RPM and put it in Yum and stuff, but it's on our wish list.
Yep.
All right, very good. Thank you. And there were a lot of questions, so be sure to hit both of them up during the break if you wanted to ask them questions. So moving right along, we got Alexander and Ang Lee from right here at Google.
Hello.
Take it away.
Is this the clicker?
That's it.
Sweet. Oops. Okay. Cool. This is apparently multi-device testing, so I'll try and talk about that, I guess. This is Ang Lee, and I'm Alex. In the interest of time, I won't try to pronounce my last name. And we're going to be talking about multi-device testing and end-to-end tests, especially for the mobile environment, the way we do it at Google. And this is, to us, this is an important topic because there's a lot of end-to-end test cases that have to do with mobile devices. The mobile devices need to talk to other devices. They have Bluetooth connectivity, they have NFC connectivity, they have they have server jobs that are running, they have other hardware you might want to interact with. And we've developed a framework that kind of covers all of these use cases, which I'll get into in a moment. So basically what we're going to talk about is, what are we doing? Why are we doing it? Have we considered not doing it? And the most important is, can I do it too? And to skip ahead, the answer is yes, you can do it too, because the framework is open source. So I won't harp on this. This is the food pyramid of testing that you've seen like 4 or 6 times by now. And end-to-end tests, of course, is the meat and sweets area that you should use sparingly. And unit tests are the bread and the veggies and stuff. So I won't harp on this because I'll sound like the FDA, but our framework is focused on the end-to-end test part. And there is a good reason for that. Unit tests are very important. You have to have a lot of them. They're your primary testing type. But especially for mobile devices, end-to-end testing is very important because, like I mentioned, end-to-end mobile devices interact very much with things around them and the environment. They might want to send data to other devices, peer-to-peer. They might want to discover what's around them. They want to discover a Bluetooth beacon or another device. They might want to talk to a device in the Internet of Things. They might want to talk to a light bulb or a fridge or a VR handset or a watch. You might need to care about what your network is. It might be cellular. It might be Wi-Fi. It might be a low-quality signal. It might be 2G. And your app might behave differently in those conditions. It might behave differently under bright lights or under low battery conditions or on a low-spec device versus a high-spec device. And depending on the performance of your network. And of course, you also probably interact with some sort of cloud backend service. You receive data from it, you send data to it. So you can't test a mobile app in isolation just by itself and have a good picture of how this app will work for users. But the thing is that that's what we do, right? So most frameworks that exist for mobile testing are very much single device based. You create an instrumentation or a JUnit of some kind, sometimes not even a mobile JUnit. You use a roboelectric, which is fantastic for testing single units and is very important for making sure that your algorithms work and for mocking your dependencies and things like that. But ultimately, it doesn't answer the question of does the whole app work. And even if you don't use roboelectric, you can create a JUnit that runs on device or using Espresso or UI Automator or something like that and run your test. But you're restricted to just the device that you're on. And we've seen presentations about labs that allocate you a single device and your entire environment is restricted to that device. So using multiple devices is step number one for end-to-end tests for mobile devices. Other issues are you need to trigger complex actions on multiple devices. You might want it to start connecting or sending a message, or connect to Bluetooth, or switch the orientation, or start scanning or something like that. You might want to trigger your own SDK or make a call in software that you wrote, like arbitrarily complex things that nobody can prepare for you. If you have multiple devices, you need to synchronize them. So you have one device that sends a message to another device. You wait for it to be received, or place a call, decline the call, make sure a voice message appears, for example. You might need to drive a wide range of equipment in your tests, so you need to somehow handle the drivers for that, the way to synchronize with that, how to talk to the hardware, making sure it's hooked up to the device, making sure it's allocated together with the device, making sure that, if you have an attenuator here and a phone here, you don't think those are somehow related in any way. You have to group the devices together. And of course, you need to communicate with cloud services, like I mentioned. And when you're done, you need to collect the debugging artifacts and logs from all of those different places to get a consistent picture of what your test actually looks like. So we've tried very hard to address some or all of these issues. And to do that, we've created a framework that we call Mobley. It's open source, and you can use it too. And to tell you more details about that, I present you Ong Lee.
Thanks, Alex. Oh, it's weird to hear yourself. Hi, I'm Ong. I work on Android OS. As Lex laid out, we have a mountain of problems that we need to address. So we created this framework, and we chose Python because it's very descriptive, and most of our developers probably don't want to think about all the crazy language stuff. When you write tests, you just want it to work. You would prefer to write in English, but unfortunately we couldn't do it today. So our test logic runs on the host machine. Because when you're coordinating multiple devices and many different types of complex interactions, it's much easier for a human to read a piece of code, say, oh, this is what this code do, as opposed to separating 10,000 different places. It also makes the debugging much easier since you have a single point of logic. And then we bundle it with some essential libraries that you can use right off the shelf. Obviously, being out of Android, we do Android device very well, as we'll demonstrate later. We also have some RF components like attenuator and monsoon. We'll open this code up in phases. And we also make it very flexible and pluggable. As you've seen on this conference, there are everybody has their own build system and workflow in their company, and you probably don't want to throw away everything you have just to use one thing. So very much like the Open HFC guys this morning, our stuff is also a library that you can easily integrate with your workflow. And it's open source. So we've been actually running this inside the company for a year now, and there are about a dozen different products that runs on this platform, and we think it's mature enough that we want to share it with you guys now. So this is the basic architecture. As you said, we don't deal with test allocation, device provisioning. This stuff, we leave it to your existing system, or as you know, like TradeFed, these established systems. Then we focus on the part that exposes these devices to you in your test script. So Mobley runs on the computer, and it just basically it's very similar to the Python PyUnit format with a few caveats, because we found out that unit test frameworks don't necessarily satisfy the system testing requirement. For example, you probably want some device recovery logic to be executed if something goes crazy wrong in your test. So we build those callbacks into the system. And also probably simple assertion may not be sufficient for device testing, in that you probably want to attach extra information in what went wrong, the device stats, or some numbers in your assertion while you leave the test. So we've built that too. And as Alex mentioned, so in our concept, our tests don't operate on a single device or a single entity. Like we operate on a collection of them, and the collection can be composed of really anything. It doesn't have to be just like consumer electronic devices. It can be some equipment in very close to hardware domain, or it can be some software service that's in the opposite direction. So we codify this concept called testbed in our framework. The testbed is just the unit of things you operate on in your integration test. As you can see, it could obviously has mobile devices. It could have 1, 2, 3 multiple Android phones. Then it could have RF components, attenuators, or call boxes, and simulate the entire telephone network. Or it could talk to cloud services like App Engine or your own backend than your app uses. Or we'll even have teams testing like network switch backend using this framework inside the company. And then we'll just go through, I really like Adele. We'll just go through a simple test just to show you what it looks like. So before that, we need a config file. The config file just describes what the testbed is composed of. It can be, here we're just having, this is just a syntactic sugar to pick up all the Android devices. Then this is the code. It looks very much like a PyUnit test. And you set it up. And in the setup process, you are declaring your hardware dependency. So the test can, if you don't have this device, we will fail. We won't execute. Then you basically here we're declaring we need an Android device here. And we call it dot. Then we make a toast on it. And when you execute it, it will execute exactly like a Python unit test with a config file. So there are some other cute features we added in, like, most of the device tests will require tons of parameters, and you can pass it in easily. Or we have a more sophisticated way to declare Android device dependencies. Let's say you have a test, then certain Android device play certain roles in this test, and you want the signal somehow correlate that information to the test without hard coding the serial numbers. So that's the design there, and you can attach other values like phone number. You may think, why do I need to attach phone number since Android should have that API? Well, it turns out it doesn't work very well, that API. So we have this because we have had so much time to run internally, we added these cute features like, I just want to log something related to this device. We have this special logger inside the Android device object that you don't have to always log your serial numbers. So as I promised you, we're from Android. We do Android very well. So in Android, there are many ways to control an Android device. It's not just, so obviously you have the ADB, that's the basic. Then you have the UI Automator. We're using the UI Automator open source project here. Then you get into most people kind of stop here. But it's certainly not enough for Google to be able to test our platform. So we added all these other ways to test to do deep dive into the system. And all this control comes in the single object. So that object has flexibility to accommodate this, and without your test having to look like 4 different handles to the same device, then you have 2 devices, just goes crazy. So Alex will talk more about the Java control here.
Sure, thank you. So as Ang mentioned, the point of having devices in your test is to control them. There's lots of ways we can control, going to do a deep dive on them. But just in general, I want to say that different multi-device frameworks have different approaches to controlling devices. So last year in 2015, we had a very interesting talk by Uber about how they did their multi-device control. And just today, we also had a very interesting talk about, actually it might have been yesterday, Intel's approach. And both of those approaches were decentralized. So the main logic was on the device, and you would use sort of a signal and slot system or a locking system to block and then wait for something else to happen. And our framework actually takes the opposite approach. It's centralized, and your test logic is on the Python side. And we feel that it's a lot easier to manage the dispatch and return and synchronization of multiple devices, and the debugging, because all of your code and logic is centralized. But it makes it a little harder to dispatch particular logic. So the first step to dispatching logic is Android API calls. There's a rich Android API. It's in Java. It runs on the device. You might have multiple devices in your test. How do you trigger actions? So there's an open source project called SL4A, which stands for Scripting Layer for Android, which basically exposes the Android API as facades. It has essentially an RPC calls, and we have integration with that. So we just call an RPC on the SL4A side. It's an app that you install on your phone. So Make Toast in this particular example is an RPC that's defined by SL4A. You call it, and internally it'll implement the call using the Android API and return back. And we have created a special extended version of SL4A, which is also open source. It's available in this link, which you can find on the GTAC website after this is over. And it will essentially expose also the system and hidden and private APIs. If you want to do system testing or Bluetooth or Wi-Fi or airplane mode, all that stuff, it'll allow you to call those methods. But this is just the Android API, which is not sufficient because chances are you're not developing Android and you have your own app and your own SDK that you care about. And also because SL4A requires system privilege, which could require installing an AOSP build of Android. It gets kind of hairy. So to do that, we have custom snippets, which are custom, basically just like SL4A callbacks, but you write your own code and you expose that to the RPC server. So on the Python side, you can invoke your own Java code at any time. And now you can use it for your own SDK calls, like JUnits. You can use it for Espresso, whatever else you want to run on the device. This is a very simple example of the Java that you might write. In this situation, I just wrote a Java function that appends a prefix to an input integer. Of course, in reality, this would be much more complicated. It might be an SDK call or something. And I extend the interface snippet, which is very bare. It just basically has the shutdown method in it. And I tag my method as @RPC, which is what allows the system to find it. And then in your manifest, you just declare the particular classes that happen to have snippets in them. And then you build it into an APK, and you added our library to it, which we will very soon expose on Maven Central. This won't work yet, but it's under the last stages of review. And just by including this jar into your APK, into your Android tests APK, you will get all the functionality the RPC server required to make these calls work. So when you build the APK and install it on the device, that is the APK with the RPC server. On the Python side, you just call load snippets, which will go and start up that app with that package name, connect to it, and then automatically find all the methods in it that are tagged with @RPC. And then in your Python code, you just call get foo, and there is your answer. Foo2 was what your Java logic was. And you can use this, like for Espresso, for example, in this situation. You can use it to drive your app. You can use it for arbitrarily complex things. But there's more in the world than Android devices, so you might want to hook it up with your own toys, with your own hardware, and we'll tell you how to do that.
Thanks, Alex. All right, now you can wake up the people who don't work on Android. So as Alex mentioned, you probably want to have your own robot, your telepresence magical machine to test to involve in your test. So like this morning, you saw the approach of the plug walls in the other frameworks. So we kind of thought of the same thing. We want to make it very easy for you to migrate your code over. Likely, you probably have something already working. So we intentionally did not choose the inheritance way because I know programmers really don't want to change their code, and especially the basic inheritance, and it's kind of hard to do in Python. So we have this very loose interface in the Python module. You just tell us how to create your object, how to release it, and how to get information from it. So for example, let's say we have something like a car. Then you just, same as Android device, you declare the dependency on its registration. Then you can move on to do actions on it. And I know it's not much, but like for various devices, you probably have various levels of controls or protocols. For example, some goes through PySerial, some goes through the USB protocol. So the pre-bundled libraries kind of provide examples on how you can interface different kind of devices. The design pattern there is there for you to kind of take a look and see what you can take away from that. And with that all said, we have a video to show this in action. So I just explained it because the video doesn't have any narration. So you'll see three devices. You'll see 2 phones and 1 wearable. And one of the phones will make a voice command, and the wearable will take the voice command and interact with the other phone. So
make a phone call, Daddy.
Oh, the audio's not working. So this is the phone says call Daddy, and the watch calls Daddy. And you can see now it's placing the call, and the other phone gets a call and just hangs up. I don't want to talk to him. Yeah. Go back to the slides. Right, so this is actually written by some just random team inside the company. We've never talked to them, just read our docs and wrote it, and they demoed it to us. We were kind of, oh, wow. So this just shows you how easy it is to use it. And this whole test is probably less than 50 lines, and including the assertions and stuff. So, and coming soon, now you can wake up the non-Android people. We are working on iOS very hard, but yeah, it all depends on what Apple lets us to do. So then we're bringing async events into snippets because most actions on Android are callback based. So it might be useful someday. You might want to have some async logic. And we also want to provide a single set of libraries for you to interact with Android because not everybody wants to write that 20-line function to connect to Wi-Fi. And it's kind of sad that it takes 20 lines to connect to Wi-Fi in Android too. And that's it, thank you. And we have some sources. Our repo just went online like 2 weeks ago. So we'll keep pushing documents and codes through, but it's just the logistics from pushing code from internal to external. Yeah.
Mobley is already up. The snippet lib will be up in the next few days, going through the final stages of review.
Excellent. Thank you, Alex and Ang. Just a note, after this talk, we're heading into a break, so if anybody needs to get started on a break, that's what will be coming up. But we'll go through some questions until then. First of all, how does this compare to everything else we've seen at this conference?
Right. I suspected that was going to come up. We didn't actually know each other until we met here. So I actually talked to them. They're very focused on the hardware teams that actually have to deal with manufacturing and stuff. We are more focused on the device side and like apps, libraries, these more higher level stuff. And we have that's kind of the focus. And our approach is slightly different. For example, the class inheritance. And also, we don't ask you to declare your hardware dependency for every single test case, which is kind of the case in HTF. Just these small things. We do look forward to collaborate, since probably not everybody have to write the same library twice in slightly different formats. Yeah.
So there's kind of 2 pieces. There's the test runner that actually kicks off the test, collects results, and things like that. And then there's the set of devices and APIs that it ships with. So there's actually, it seems like there's a lot of overlap between OpenHTF, the runner, the kicker off, and the Mobley runner, which would be collaborating with them quite closely. But in terms of the bundled library, it seems like they're more focused on hardware devices, like Ang mentioned, whereas we're focused a lot on Android and APIs and software and being applicable to app developers, not hardware developers. But we'll be talking to them.
Very good. Always good to talk it out. If there's any questions in the room, go ahead. You can raise your hand as well. I think we covered that. Can we use the real devices and emulators, simulators, both with it?
Yes, because we don't really make assumptions. So our controller for Android device really just takes an ADB connection. And if you have an ADB tunnel into your simulator, that's fine. And we're also working with some other team to cook up something really cool, but I can't really say that. Yeah, but real device and simulators, a mix is fine. Yeah.
Yes. What's the biggest challenge in taking this from internal to open source?
Internally, there are a lot of magical tools in Google that we don't have to write, and yeah, but open source, then we can't. We're still just figuring this out. Yeah.
There's a big set of utilities that we have internally that are pretty closely tied with other utilities that we have and particular teams that are working on them that are changing them all the time. So the process of trying to abstract that into a public, stable, useful, consistent set of utils for the open source release is something that's still ongoing for sure.
Yes, it is very hard to do, I know that. What about the test result? Do you have any dashboard available?
So the framework is designed to integrate with a test runner, so that's why it doesn't handle things like device allocation, shipping files around, and sending results back. The results go firstly into the summary JSON file that is part of your log directory for machine parsing, and secondly, the test case itself is executable, and the exit code of that execution is non-zero if the test failed, just like PyUnit would be. So we're hopeful that wherever you can sort of plug in PyUnit or a generic command that runs a test, you should be able to plug this in. We're definitely working on better integration with test runners, which will provide dashboards and results and execution and things like that. It's a little hard to focus on it because we have tools internally that we're all already using that are excellent, but that we can't release. But we're going to try and make something in the future.
Okay, I think we'll do one more before the break. Is the configuration or implementation easy as compared to another open source tool?
What's another
one? Or did you make your configuration so difficult that
personally, I can say it's pretty easy because I'm a very lazy person. I really don't want to have to go write 3 different files in different formats before I can run a test. That was just too difficult for me. So we just have this one config. It just really describes what the testbed has and how to find it, like say a unique serial number to your device or a network address. So that's really all we want. You can go as crazy as you would like in the config since it's just a JSON. We do have teams that do that, where the configs are just like, they would encode the entire encryption key in basic C4 string and tons of them. So yeah, but for me personally, I prefer to stay on the easy side.
The config, you can attach your own parameters to the devices. You can create your own devices and their own config keys, and you can have params at the top level that just get passed directly into your test case. So it is very configurable. And the basic config, as you saw, is very simple, and it can get arbitrarily complex. So it's quite configurable.
Great. Well, yes, that brings up a good point. When choosing a testing tool, make sure the developer was very lazy beforehand, and that's a good signal that it'll be easy to use.
Until you need bug fixes.
Yeah, one thing at a time. All right, another hand for Alex and Hank. And we'll head into a break for a half hour. We'll start again at 4 o'clock. Pretty simple. Everybody's figured it out so far. Yeah, once I get there. All right, welcome back. We are in the home stretch. And there's still a big crowd here, which is good to see. So it's glad everybody stuck around. Is everybody ready for the final end game? I got no reaction. Let's hear it. Yeah, GTAC 2016. This is it. At this point in the show, I don't have any jokes left. So again, I apologize. Some would say I never had jokes in the first place, but hey, let's, what I can do instead is I've got assistant with me, so I can have assistant take care of this. Here we go, let's live demo. Everybody be very quiet. Let's see if I hope this works. Tell me a joke.
Okay, here you go. If a short psychic broke out of jail, you would have a small medium at large.
All right, way to upstage me. Leave it to the assistant to upstage me. All right, enough of me. Let's get into our final block. We have Jitesh and David from the BBC, and I'll hand it over to them.
Hello, everyone. My name's David Buckhurst. I'm an engineering manager at the BBC, and I look after the teams that build our TV applications, console, set-top box apps.
My name is Jake Gossai. I'm the test manager for the Titan team, which is the BBC's test tools and infrastructure team, and we bring software engineering skills to our test department.
So we work for BBC Design and Engineering, which is the technology group within the BBC. So people think of the BBC as a broadcaster or a news outlet, but to me, the BBC is a great technology innovator. And so 80, 90 years ago, the BBC was there, big part of the development of TV and radio broadcast technology. We had our own computer in the 80s. Robotics is obviously a big part of what we do. More recently, I guess the internet age, we were one of the very first companies to have a video on demand application in iPlayer. It's been around over 10 years now. So I think the last time I counted, we had about 30 mobile applications and 4 TV apps across a whole range of the devices, which is kind of what we're going to talk about today. In trying to scale our automated tests to cover as many devices as possible, we started to learn the real challenges and actually the value in test automation and where that value was. So one of the things that makes the BBC unique is the way that it's funded. So we're publicly funded. It's not a government tax, but a license fee. And that gives us a very large remit that's established. Our mission in the Royal Charter is signed by the Queen. This is the one I keep on my desk. But basically, our mission, which is inform, educate, entertain, there's 2 very important parts which is very relevant to what we're talking about today. So our focus isn't on profit or growth, but in value for money and reach. So value has to be a big part of everything we do, and also reach. So specifically something we refer to as the universal obligation. So what that means to us in design and engineering is that we have to ensure that our services are available to as wide an audience in the UK as possible. And so if you think about smartphones, TVs, and we've had other speakers the last 2 days talking about device fragmentation, we can't actually just choose which devices we support based on capability. We have to get our apps to work on the devices where the audience is. So that means it could be a $50 tablet or it could be a $5,000 smart TV. And in fact, we started really to become overwhelmed by the challenges of manual regression.
So to get us started, we start with behavior-driven development, or BDD, to first understand exactly what it is that we're trying to build. And what we started to do was run 3 Amigo sessions. So we got our developers, our testers, and product owners all come together and collaboratively understand exactly what it is we're trying to build. With this, we'd then produce a feature file. This will list the key scenarios or acceptance criteria for that feature, and we use this as a starting place for what we were going to automate. And we got pretty good at automating this way, and we got them running on physical devices. But the problem was, we still had these massively long-running regression test cycles. So what we wanted to do was take these automated tests and actually run them on as many different devices as possible. This way, if those tests passed, not only had we satisfied the acceptance criteria, but now also had an executable specification. So we got pretty good at doing this, and so we came up with some quite innovative solutions. Here, one of our dev teams actually grabbed a load of phones that they wanted, grabbed a spare chair and a laptop, and actually stuck it to it, and would actually move around a mobile device testing rig. So they could actually wheel this around to wherever they were, run the tests, and actually deal with any issues that came up. Problem was, this wasn't very scalable. I mean, we had 20-odd development teams, and building a test rig like this for each one wasn't really going to work. And also, each team would then actually have to reinvent the wheel every time, understanding how to get the test to run on all the different devices, deal with the Wi-Fi issues, the stub data issues, and generally just having the devices in a state that would run the automated tests. So what we did was we created the Titan team, which is this test tools and infrastructure team. And these are software engineers embedded within the test discipline to help build test tooling and infrastructure for the test department. And one of the first things we got these guys to build was a test rig, which they called the Hive CI. And they build, maintain, and run this for the whole of the BBC, and it gives us 4 main features.
So yeah, so one of the big things that the Hive does for us is it just keeps devices in a state that's ready for testing. So if anyone's done a lot of trying to run automated tests or even just do manual testing on device, well, the first challenge is find the device. It's probably hidden in a drawer somewhere. Once you've found it, you have to then charge it. You have to get it on the right Wi-Fi network. You then have to clear off the SD card that's been filled up with screenshots. And so what we really wanted was a system where we could just plug a device in and it'd be ready to go. So the picture here is actually for our TV applications. So what we do is this is essentially a holding app. We can launch a television into the holding app through basically broadcast hooks, and then it's ready and waiting to run tests. So the second thing that the Hive does for us is inventory management and monitoring. So, no good just having all these devices there if we don't know what state they're in. And really, we wanted a totally zero-effort approach to having an inventory of devices. So we can literally just plug a device in, it registers, we know what the type of device it is, we know what state it's in, and we're ready to go. And also, so you can see a number of those devices are red. They've, whether they've fallen off the network or the Wi-Fi's gone flaky or the SD card's filled up, someone can go and investigate that device. And importantly, they stop running tests. But also, I mean, more recently, we've got a bit more advanced, and some of the devices, they can actually recover, so they'll try and clear off the SD card. They'll try and fix the Wi-Fi settings. And I guess a real key thing that the Hive does is actually run those tests. So teams anywhere in the BBC can write tests. They can then choose which tests they want to run on, which devices they want them to run on, and then the Hive just manages that scheduling for them, so they don't have to kind of worry about that bit. And it'll also do things like retries. So if there's flaky tests or anything like that, it'll retry them. I think we allow a single retry, don't we, for every test. And importantly, because it's like every team across the BBC, all building apps, they're all using different frameworks, so it really has to support any type of framework that people be using to automate their tests. And then a final kind of the fourth big thing that the Hive does for us is just result collation. So if you imagine for a release of iPlayer, our video on demand app, we might have 100 to 1,000 different test runs. We want to bring that together in a view so you can just see at a glance, oh, there's no failures, or if there are, you can drill down and investigate them. And also, it smooths out any flakiness we've got, so that the developers don't have to worry about where our tests might not be so solid. So this is an example of JIT's team setting up one of our TV hives. So we found this corridor that didn't seem to be in use. It turned out it was a fire escape, but it's an absolute brilliant place to build your testing setup. So, and that's just running all our TVs on the holding app. They're ready to run tests. In fact, some of them are running tests. This is kind of more typically what a mobile hive might look like. So we can kind of set these up anywhere, just inexpensive PC hardware, running Linux and our hive daemons, and just plug in a device. It registers, it's on the system, it could run tests. And then for iOS, we do the same with Mac Minis.
So we started to get pretty good at writing automated tests, maybe a little too good, and a lot of our dev teams were starting to struggle with exactly what was in these test suites. They had so many now that they didn't understand what was and wasn't tested anymore. We also started to drown in a sea of flaky red tests. Whenever anything went wrong, they wouldn't know whether it was an actual defect, an issue with the test framework itself, or actually an infrastructure issue. So, and the burden on these teams just to try to maintain these tests was getting bigger and bigger, and the value that they were giving was just getting less and less, and they were starting to ignore them. So we looked into seeing what we could do next to try and see, how can we help these teams deal with this test automation issue that they're having. So we went back to the test pyramid, and we looked at the automated tests that we had, and we looked to see how many of them we could push down into the integration and unit test levels, where they'd run a lot faster, a lot more reliable, and a lot easier to write. But we did want some automated UI tests. We were trying to create the peak of the pyramid. And we started speaking to our dev teams, and they all mentioned that they were running a small suite of tests all the time. It's kind of like a core suite of tests, or smoke tests. They all had slightly different names for them, and they all had slightly different tests, and some were bigger suites, and some were smaller suites. So we looked into these principles that these guys were running and created a new term called Puma tests. One of the first things those teams said is, what the hell are Puma tests? Well, it's actually an acronym. It stands for Proves Core Functionality, Understood by All, Mandatory, and Automated. So we take the first two, proves core functionality. What is the main thing your app should do? For us, our app was a video on demand service, so it's video playback. It doesn't really matter if you can add it to favorites, download a program. If you can't play that video back, your end users are just going to leave. So what is the core thing your app should do? Understood by all. Our dev teams didn't understand what was and wasn't being automated anymore. So it's up to those teams to come up with those tests themselves. But not only that, everyone within that team must be able to execute those tests, whether they're technical or not. And also the status of those tests should be visible to the whole team, either via our dashboards or email notifications. Mandatory. It's got to form a part of your delivery pipeline. Whenever developers commit any piece of code and an app is built, the Puma tests are run. If those tests fail, everything stops dead. You don't get no release, nothing gets pushed to live. It's up to the team to then debug those tests and figure out exactly what has gone wrong. And last but not least, automated. It's got to give you fast feedback. It's got to run in 5 minutes or less, and it's got to run on representative devices of your end users. Now, one of the key reasons of calling them Puma tests was it gave the team a common language. When they said, what are your Puma tests, they knew exactly what they were. But it also stopped them from putting in tests that weren't related to Puma tests. So any other suites that they want to create, they could create them, but it keeps the Puma suites very small, focused, and fast.
So Pumas were a big success for us, and when we were looking at the kind of 200-odd tests we'd have that were across the whole UI and trying to boil that down into sort of 10 really useful core tests, we started to look a bit more about what we were actually testing and what was that core focus of the application. So thinking about a video-on-demand app, video playback is surely the most important thing that we're actually validating. And what we realized is that although we had tests that took every single journey to the play button, there was nothing that actually pressed play and validated that playback was happening. So, and part of that was because some of the automation frameworks we were using didn't really support that kind of journey, that kind of testing. So, but instead of spending all the effort in building out all these applications, focusing that time instead on just building some simple libraries that would help us do things like confirm, is video actually playing back on this device, or is audio coming out of the headphone jack? So as well as kind of focusing our core test to the stuff that was really useful, we also started to think a bit more about the kind of tests that are actually really useful to run on devices. So things like performance tests, where actually you do want to be able to run those on devices and see what the difference is. So for example, live video is very important to us. So we were looking at what are the start times for live video playback, and that was just information we didn't have before.
So when the Hive wasn't running automated tests and the testers weren't actually using the physical devices, they weren't actually doing much else. So we thought, well, why not use these devices to run tests every couple of hours and give us performance feedback on what our app was actually doing? And so to try and help the team keep focused and have a common language of what these types of tests should be, we came up with a new acronym, again following the CAT theme, called LION, or Live Insights and Operational Notifications. The idea behind these tests is to run every hour, and these will give us data on how long did the app take to start, how long to video playback, does video playback, how long are our core journeys taking, and then putting canary tests around these areas, or threshold type notifications. So if it went above or below a certain mark, it will inform the team straight away and let them know that, oh, their app's performing in a different way. This way they didn't have to wait for the end users to tell them, but they actually had these tests running constantly throughout the day across a representative devices. As David mentioned earlier, our remit is to reach a wider audience as possible, and so we need to make sure our app is accessible as possible as well. This is a picture of one of our colleagues, Ben Mustel-Rose, who has actually helped us build a lot of accessibility testing and actually automate some of the feedback loops around here. So what we do is we've leveraged the Hive to actually use screen readers as devices on the Hive, and what we can do is we can actually send our Puma test to the Hive, enable the screen readers, and then capture the output, and then compare that against a known set of good output, and then report the difference back to our dev teams. Now, it's not necessarily automating accessibility testing, but what it does do is it gets our dev teams thinking about accessibility a lot earlier than they did before. Whereas before, they'd actually release the app and then wait for feedback from the external users. Now they're thinking about it every time they're committing a piece of code and producing a build and thinking, hold on, how is this affecting this core journey? And letting them think about accessibility testing a lot further down the stream.
So to iterate some of the points what we said, so it's all about value for us. So, and the last kind of 4 or 5 years have been this journey of discovering that in trying to scale our automated testing, we were kind of missing the point of the value of them. And I think those learnings are really kind of 2 things. So one is to focus certainly your UI tests on the absolute core journeys and push everything else down the pyramid. And the second one is to focus on the things that are really valuable to run on devices, so performance tests, compliance tests, and that's where you really get the return for the amount of effort you have to put into this kind of thing. So if you want to find out more about our approach or tools, check out our open source website. So everything we've talked about today, it's developed in the open on our GitHub BBC org. So if you want to set up your own device cloud internally, or you just want to look at our Puma approach or try out some of our libraries, please give it a go and talk to us if you've got any questions. Thank you.
Thank you.
Great, thank you both. Let's go into questions. I don't have any witty comments at this point other than to see, I guess, across the pond, there's a lot of the same issues we run into.
That's right.
What do you use to automate actual video playback verification?
So, what we tend to do is a very, very simple approach that just works across as many devices as possible, which, an ADB screenshot frequently to literally just capture, every half a second images. Are you getting enough of a diff that you can confirm that video is playing back? And that's actually been amazingly successful. It can spot when we've got buffering problems. It can,
yeah, exactly. It's been really good. You'd be surprised at how the diffs actually have a unique fingerprint. So we've actually been able to identify when a program's actually starting and actually how one program's different to the other. So it's been very simple, but it's worked surprisingly well.
Yeah, we've not found we needed anything more complicated than that. No. It's really fulfilled everything we needed.
When are you going to open source it?
It's all open source.
All open sourced. Oh yeah, was that on the last slide?
Yep.
There you go. I am paying attention at this point, so Some images of your player show that it supports cast. How do you test cast functionality?
Same way most people do, by actually setting up a cast and connecting to it. We haven't actually managed to automate this yet. We've had all sorts of issues within our own buildings with Wi-Fi networks and casting to different casts themselves. So right now, that's still very much a manual process. We have some stubs within the app which will mimic a cast being there, and so we can automate the functionality of it. Or does the cast button show? Does the cast button not show? Do our hooks within the app which kill cast on and off work? But the actual casting of it itself is still very much a manual effort. What we found is actually we still need a human person sitting there telling us actually not only does it cast, but the experience of casting is actually as good as we expect it to be. So I mean, we can automate it, that's fine, we can know it would cast, but it still doesn't tell us how good it is. And it's no good if it casts to a TV and then we don't know if it's actually playing anything, or the audio is not there, or it's stuttering, or it's just a really poor experience.
Any questions in the room? I'll head over that way, but how about 4K playback? How do you test?
Not got any 4K playback yet, but that's something we are working on. Yeah.
Hey guys, so it's really interesting. I'm from the app business over in King's Cross, and we've literally got the same problem, and we are working on something to do with testing as core journeys and stuff. And it seems a lot of other people have hit the same snag. Why do you think it's happened now that we're starting to see this whole scale versus value, and that we're having to look at picking and choosing the right tests to run?
Do you want to say that? So for what we found is 4 years ago, everyone said, look at the test pyramid, and it said, push everything down into the lower levels. But before, say 5 or 6 years ago, if you wanted to automate anything on mobile, you just couldn't do it. And then all of a sudden, all these tools started showing up: Appium, Calabash, and then now native support via Espresso, Robotium, Xcode UI testing. So everyone just went pretty much mad and thought, right, we can automate the hell out of all this. And not only that, we don't have to get our developers to do this anymore. We can, outsource this to test engineers or software engineers to test, developers and test. And so what we all did was built loads of automated UI tests. Because it was easy, well, it seemed easy, and we can just build more and more and more. And then you started running into problems of, hold on, how do you run this on so many different devices? How do we, bring down the test times? We can parallelize it as much as you want. You can stub out the test data. You can do all this. But actually what we realized, none of this was actually helping us. Bugs are still getting out there. I mean, the automated tests only check a very thin, narrow path of your app. Anything beyond that, it's not going to check. And also what we found was, it wasn't telling us whether or not the experience was any good for end users, whether the video playback was of a good quality for us, or audio playback was of any good. So what we started to realize was few core tests were actually telling us the most. Does the app start? Can I get to the main features of the app? Can I hit the play button? And actually they were good enough. And we can push a lot of the other testing lower down level, and then actually have our people testers, our manual testers, or beta test programs tell us exactly how it's actually performing, and do people enjoy using it. So I think that it's been a journey for a lot of us. Even though we all knew we should be pushing it down, we all kind of tried it and gone, okay, no, this doesn't work. I've been fortunate enough to talk to a lot of other organizations, and they've all hit the same thing as us, some only having 3 main automated UI tests and saying that's enough for us. So that's my 2 pence.
Very good. Well, thanks, Jitesh and David.
Thank you.
We actually have a little bit of time for a break, and that will help us set up for some demos for the lightning talks as well. So we will start it up again at 4:30. All right, if everybody has their afternoon coffee and tea, we're going to jolt you back awake with some fast-paced lightning talks to close out the conference. I hope you noticed that we did plug in the computer before it died, the question computer. I know that was, everybody was worried about that, but yes, it is charging right now. So next up, we have Kostya. Going to give a lightning talk.
Good afternoon. I hope you are a little bit awake. But to make you more awake, let me ask you a couple of questions. First of all, how many of you care about C++ applications, stability and security? Too little. Everyone, please raise your hands, because you do care about stability and security of C++ applications, even if you don't develop them yourselves. How many of you have fuzzed something in the past, C++ or not? Okay, at least some of you in the audience know what fuzzing is. I'll talk about fuzzing, and I'll talk about one particular tool to do fuzzing, and I'll have a tiny live demo today. So what is fuzzing? Why do you want to fuzz? What do you want to fuzz? How do you want to fuzz? A little bit about the particular fuzzing tool and the live demo. Let's go. So what is fuzzing? You can define it in many ways, but essentially it is an infinite loop of create a test input for your application and feed it into your application. There are two things you want to get out of fuzzing. First, you want to crash your application. So if you crash your application, you found a bug. Even if you don't crash your application, you still grow code coverage overall, and you can use the corpus you've grown for regular regression testing. Why would you want to fuzz something? First of all, C++ offers you many unique ways to shoot yourself into the feed, like buffer overflows, use of the free integer overflows, and some such. And fuzzing is a very efficient way to find such C or C++ specific bugs. But even if you're not using C++, and you're using some safer and slower language like, I don't know, any other, you may still have divide by zero, you may still have null dereference, you may still have assertion failures, you may have concurrency bugs, you may have bugs that cause your application to consume too much resources, CPU memory or network bandwidth or whatever. Sometimes actually fuzzing may allow you to find logical bugs as well. What to fuzz? The usual suspect for fuzzing is any application or any library that consumes untrusted data. So anything that consumes files from the internet or from users, anything that monitors the network activity, which accounts to more or less anything, right? There are two specialized targets, operation system kernels and UI applications, and I'm not touching those two. How to fuzz? One of very popular ways to fuzz is to apply some kind of application-specific generation-based rule. For example, if you know the syntax of the files that your application consumes, you can generate files that follow this syntax. And this approach has been very, very useful in many cases at Google and outside, but I'm not touching this today. Another approach is called mutation-based fuzzing. This is when you already have a set of valid inputs or invalid inputs for your application, and you start mutating random inputs in random ways and feeding these inputs into your application. And sometimes mutations could be as simple as bit flipping. Sometimes mutations are much more complex. And this approach is also very powerful, but if we make a little, one tiny step to improve it, it will become much more efficient, like orders of magnitude, and we've seen it in many cases. So the tiny step is called guided mutation fuzzing. And by guided, I mean that we use code coverage to guide both the mutation and the extension of the corpus. The workflow is as follows. You build your application with some kind of coverage instrumentation. So every time you execute an input with the application, you know what parts of the application have been touched. And then you start mutation fuzzing. If some of the mutations caused new code coverage to appear, you say, oh, this is a good input. It touched part of application that the rest of the test corpus didn't. So we add it back to the corpus. And we have lots of evidence that this increases the efficiency of fuzzing by several orders of magnitude. Come on. Yeah. We are working, we meaning my team right now, are working on a very specific way of fuzzing. We fuzz C and C++ APIs or libraries. We do not right now fuzz large binaries. We do not fuzz services. We fuzz small or medium-sized API entry points. You can think of it as unit test-like fuzzing. So we define a thing which we call fuzz target, which is a C function that consumes bytes. And inside that function, you can do whatever you like with these bytes. Basically feed these bytes in one way or another into your library. We can find the bug on this slide.
It should be 4, sorry?
Yes, correct. So on this slide, you have C code that, given one specific input, will trigger a buffer overflow on the line which says data sub 3 equals Z. Can everyone see the bug? I leave it here for 10 seconds. Raise your hand when you see the bug. Come on. So fuzzer will find this bug much quicker than you. There are several fuzzing engines on the market, and the fuzzing engine is the tool that finds inputs that are interesting enough and feeds them into your fuzz target, into your application. One of them is developed by my team. It's called LibFuzzer. It's an engine for guided in-process fuzzing. Guided means that it is using code coverage, and in-process means that everything it does in a single process. It does the mutations, and it feeds the inputs into the API and the test, all in the same process. It's a library in a regular C++ sense, which provides a main function. If you want to use this library, you need to build your code with some extra compiler flags that actually do provide the code coverage information. Then you link your application with the libfuzzer. Then you, or in parallel or before that, you have to find a set of inputs for your application somewhere, an initial test corpus. Sometimes it's okay to have initial test corpus empty, but in most cases, the better test corpus you have, the more efficient fuzzing will be. And once you have this directory, you just pass this directory as a parameter to the just compiled binary of the fuzzer. This is it. Let me show you some example. This bug was made public about 3 or 4 weeks ago. It was a buffer overflow in one of the open source network libraries, CARES, and you have the CV and the names on the screen. The bug in that library was a single byte buffer overflow, which overwrote 1 byte somewhere outside of the object. It caused a full exploit of Chrome OS. So there was direct impact for Google, that Google had to pay $100,000 for the researcher who provided us the information. But there was also indirect harm, because who knows, maybe someone else has discovered this bug before and was using it against our customers. So this was a pretty nasty bug, which is now fixed. And all you need to find this bug is on this slide. Everything you need is on this slide. So count how many lines here. Can we switch to demo? Okay, so I have a pre-built binary of the fuzzer that I've just shown you on the screen. How many of you believe me that I can find a $100,000 worth bug before the end of this talk? Come on. Okay. Done. So I've started the fuzzer on a single CPU on this laptop, and this is not the most recent laptop. And it started finding new inputs. And on the very left, you may see the numbers. It's the most significant digit is eaten, but it basically executed several thousands of inputs before it found an input that triggers a bug. And the bug is heap buffer overflow, write of 1 byte. And here is where. So if someone invested 10 lines of code into finding that bug, he would find it instantly, as you have seen. What else is convenient about libfuzzer is that once it reports a bug, it also creates a file on disk which has the complete, which has the bytes that cause the bug to happen. And if you want to reproduce it, can you see it? Yeah. If you want to reproduce the bug, all you need is to feed these bytes again into your target function, like this. And it will happen again. And so you can debug it, you can verify that it's fixed, you can add this input to your regression test suite, etc. Switch to the slides, please. So I've just shown you a very, very important, very scary bug that can be found by fuzzing instantly. Fortunately or not all scary bugs are like this. For some bugs, we need to spend hours. For some bugs, we need to spend months finding them. And Google has these resources, and Google has, to some extent, humans to do this. Not all open source projects have it. And we're trying to help. So what we want to do? We want every open source project, at least every important or every significant open source project, to move away from it has been fuzzed at some point or it has never been fuzzed, to the situation when we can say this project is being continuously fuzzed, and we actually know that the coverage produced by the fuzzing is good enough. And for that, we are starting to introduce what we call OSS fuzz, open source fuzzing, which is a fuzzing as a service for important open source projects. It is based on the same fuzzing infrastructure that we're using for Chrome, and that has found many thousands of bugs for Chromium so far. It provides multiple fuzzing engines under the hood, but the user shouldn't know about it. All the user should know is how to interface, how to create a glue between their project and the OSS fuzz. And this slide, again, is an example of such glue. The project is now public. It's on GitHub. And if you own or work with some open source project, you're welcome to participate. Thank you. And I have 55 seconds for questions.
Excellent talk. Any questions from the audience? We have one.
Hi. So, in terms of like detecting like memory issues, like how does this compare against like Valgrind and stuff? Like, how much effort and time do I have to spend with this tool versus something like Valgrind, which has been out there forever?
Forget about Valgrind, use address sanitizer. But this Valgrind and address sanitizer versus fuzzers are complementary things. You cannot find bugs with Valgrind to address sanitizer just by running tests, because the tests will not execute the buggy code. You need the fuzzer and the tool like Valgrind to address sanitizer together to find interesting bugs.
My question is, how is the actual mutation done? Can you provide some details on that?
We start from bit flipping and byte flipping, those simple things. But also, as the fuzzing runs, we gather the statistics about the comparison instructions and library calls, and we actually accumulate a dictionary of tokens that are used by the input language. And then we start feeding these tokens into the input stream. So over time, it gets much more sophisticated than byte flipping and bit flipping.
Oh, well, I think that's all we have time for lightning talks, but thank you, Kostya. I'm now going to go out and find myself a $100,000 bug. Now I know how to do it. So next up, we have a great way to finish the conference, talk on testing crashing servers by Jonathan Abrahams. So I will hand it off to him.
Okay, thank you. Get the slides up. Is that on here?
No, it looks like it got hit here.
Okay. It's probably when I moved that up.
There you go. That looks like yours.
Okay, thanks.
You're welcome.
Hi, I'm Jonathan Abrahams. I work at MongoDB. I'm in the test infrastructure group. Hopefully some of you are familiar with what MongoDB does. And we're going to talk a little bit about how we test our server under crash scenarios. So as you are probably aware, machines can crash for a variety of reasons. Maybe it's in a virtual machine, or it might actually be a physical machine. And we need to see what's going to happen to our MongoDB server. I mean, it's pretty important. We're holding data that's stored out to disk, and we really don't know. When we came into this project, we weren't really sure, can we be robust enough to survive that? So there could be operating system failures, hardware failures, and then there's also application crashes of the MongoDB itself, where maybe you got some sort of unexpected termination, maybe from fuzzing. Well, we could actually try just aborting the MongoDB, which is the process of the server, but it really doesn't fully simulate what happens if you have an unexpected crash of the machine or like the operating system kernel. we really want to be able to test some sort of immediate power loss because of caching that might be done at the lowest level of the I/O, and also kernel panics can leave the application and the data in unrecoverable states. So this is your typical startup of your machine after it's been terminated or even booted. It will go into some sort of hardware and software checks in the operating system, and then eventually it'll turn it over to your application. In our case, the MongoD has its own recovery mode. It can detect the fact that it had been terminated, and if it passes that, then it allows it to be connected to by clients. So, how are you going to go about, when we jumped into this project, what are you going to do about testing something like, power failure? Well, the easiest thing is just basically run MongoD on some machine in a lab or at your desk and pull the plug and start it up again, see what happens. Of course, that's manual and labor intensive, and, you can't do this across different testing cycles. So then the next thought was, well, we could do a real low-tech, cheap solution. Let's just put an appliance timer there. You don't have to be there to actually pull the plug, but the appliance timer will do it. But the appliance timer it's not fine-grained. It's 15 minutes. You got to wait before it can actually turn it back on. So you can't do these repeatedly over and over again and get, maybe quick results. Another alternative approach, which we'll discuss a little bit later how this was done, was to use an internal command to actually crash the machine, which is almost functionally equivalent to a power cycle. And then I was able to set this up in a cron job so we can run this internal command, so everything's kind of like running on that machine. So that was another approach. So we realized we really need to do this a lot more often. So we have to go figure out how we're going to be able to do this over and over again. Because the recovery, the moment in which you crash it, it's very subtle. We really don't know at what point, what might be running that might cause something to be unrecoverable. So we want to run it like maybe, 100 times or something before we feel good about this. So we came across this solution, which I don't know if you can actually see it here. This is what we use for the power part. It's called the Ubiquiti mPower Pro. Let me see if I can turn on the light. And it's a programmable power device where you have SSH access to it. And all you do is you can go in there and you can basically turn off one of the outlets on here, or any of the outlets, with a very simple command. This is how it's done. Hopefully you can see that on the slides. All you do is you send a 0 to shut it off to some /dev/ let's say output 8, which this is plugged into, and to turn it back on, you send the 1 in there. And that's all that script is doing right now. So that was one part of the solution. We figured out how we can crash physical machines and repeatedly turn them off and on. What about virtual machines? Well, virtual machines operate differently. They use shared hardware, or rather they use shared resources because they rely on the underlying host operating system. And it's also important to test virtual machines for maybe terminations of the virtual machine, because that's what a lot of our customers use out in the cloud, or even in their own data centers. They're actually running with virtual machines. So it's important to know from a completeness perspective whether or not virtual machines are going to have any problems as well as physical machines. Crashing virtual machines actually turned out to be fairly simple. Like using KVM type of machines using the Linux containers, it's just using this verse destroy command, which is, there's nothing sent to the underlying applications running in the machine. It's like basically destroying it, but it doesn't destroy the machine from the perspective that you can't bring it back up. It just basically, it's like a shutoff. And VMware also has this VM run stop hard command. And turning them back on it's the same corollary as just running start commands. And believe it or not, they actually do come back on. I did script this, and we use both of these. And you could probably do this for other virtualization, other virtualization machines as well. So here's the other part that I did uncover about internal crashing, which works for Linux only. There's this thing called a sysrq key, which is like as if you're at the console and you want to basically put it into some boot mode. You can do this through software by writing a 1 out to proc sys kernel sysrq, sets it up, and then you send the B for boot to proc sysrq trigger. It's an immediate boot of your machine. So here's another part of where you can basically internally take any Linux machine, I think most modern ones at least, and it will just boot it right up. So it's like another type of crash. One other part that we stumbled upon was that when the machines do come back on and they're plugged into something, you have to make sure your BIOS is set so that when it sees the power, it will actually bring it back up. So that's another one of those caveats. Windows machines have some sort of additional prompting that will happen sometimes, so that was another thing I was able to script in. So I was able to actually do power cycles on Windows machines, but through the physical means. And there's a utility called BCD edit, and you can set the boot status policy to ignore those failures, so it doesn't give you these prompts like, do you really want to go into recovery mode? Do you want to boot normally? So essentially, you can just basically plug a machine into here, run some sort of script that crashes it, and whether it's plugged into a Linux machine or Windows machine, they'll come back up. Now, if you want to run whatever application, in our case MongoD, you can go ahead and run your applications as you would normally, and then do whatever tests you want to do. So we have the machine, we figured out all these key parts to it. We stitched them together into a bash script. And like I said before, the MongoD goes into this recovery mode. This is performed automatically. In the case of our storage engine, Wired Tiger, which is what I have on my shirt, which is our default storage engine now, it's going to go and look for the last stable copy of the data it has on disk from the last checkpoint it wrote out, and then it'll apply a journal log to bring it back up. It's a little bit more we want to do in the scripting. Before we actually crash a machine, we actually want to apply some sort of moderate load, or maybe more than moderate, of all sorts of different type of database commands, and to basically put the database server into any mode we can think of, so that at the time the crash happens, we'll be able to possibly stimulate a data corruption or something like that. That's what would be our failure. And in our case, that was specific to the MongoD server. We added in some other options about how we wanted the clients to do that, whether it would be in a replica set, a single node replica set, or standalone, what storage engine to test. When we started the testing, Wired Tiger was new to MongoDB. We actually had just acquired it, and it was being introduced as a second storage engine. We use mmap v1 as our storage engine prior to 3.0, and there was a lot of focus on making sure that Wired Tiger was really going to be robust enough to switch it. So after it started, like I said, we're going to do some other things, check the status of the server, but the key point is that if we fail to recover, or we can't connect to the MongoD because maybe it died or something like that, and some other validation that we can run against the MongoD once it comes back up, we know the test has failed. Okay, and this basically talks a little about the type of things that we do after we've restarted it. The validation is an additional step for those of you who do use MongoD that does not happen on recovery mode. Recovery mode is not as, it doesn't look through all the documents to make sure that it's, there's no problems, but validation actually goes through your collections thoroughly. It's a slow process, but it might be necessary to do if you do encounter this type of situation. What was good about this project is we developed a script to make it basically like a self-service application, because we had developers all over the world, and this script actually not only can run on, it doesn't need any custom hardware, it can run on Windows machines, it can run on Linux machines, it can run in the cloud, it can run on localized and remote hardware, things like that. And we'll save some data for in case of failure is detected, we'll back up data for our developers to use. computers. So in conclusion, we found that the crash testing helped to extend our testing to scenarios we had not previously covered, and to be able to provide these local and remote teams with the tools to reproduce and analyze the failures. And we helped to improve the storage layer, hopefully, for the MongoDB. Like I mentioned before, we did find some bugs there. And here's a list of some of the bugs we found. Most of them were fixed, and I think there might be one that they're still working on. One open issue that I did find that I haven't been able to solve, maybe we have somebody out here in the Windows crowd, you can easily crash, like I said, internally the Linux machines, but from Windows, you get these blue screens of death all the time, but I don't believe there's any systematic way to crash a Windows machine. If anybody knows, please send me an email or be in touch with me afterwards, and I'd love to hear about that. Thank you.
Thanks, Jonathan. So tools to crash computers. I am picking up so many great things from this conference.
Turn my light back on.
So we do have a question from the audience. How do you verify that all committed changes are present after the recovery?
All committed changes are present after the recovery. Oh, okay. So that's a good question. So that's part of the validation, right? So one of the things that one of the options that I mentioned before was I write a checkpoint document out before I do the crash, which is an optional thing, because also that can trigger certain things that could happen at the database layer. So if that doesn't show up, then we have what we call when we're in a replica set an op log. So if that shows up, then we should have everything prior to that. So that's one of the ways we're able to determine that. But if your application, want to do something like this, you probably have to come up with some ways of figuring out how you're going to be able to determine that it's successful also from recovery.
All right. Any questions in the room? Well then, thank you, Jonathan.
Okay.
All right, and that wraps up GTAC 2016. All right. All right, closing remarks. I know picking up from this year, one of the themes I saw was that we have so many testing tools available to us now that the big problem is how do we run so many tests that we've written? What a time to be alive. What a difference from GTAC 10 years ago where the main focus of testing or talking was what tools can we use to actually do automated testing. So we've come a long way. It'll be interesting to see where we go 10 years from now. Will it be how do I test, or how do I slim down all these hundreds of thousands of tests I'm running on my devices? That was my takeaway from it. And I'm sure you have your takeaways as well. You can keep the discussion alive on the attendee mailing list that we have going around. I hope you all made good connections here with all your fellow attendees. So keep the discussion going. That's a big part of what this conference is all about. Let's give a big round of applause for all the speakers we had this year. I think we had an excellent agenda, and all the talks were outstanding. So thank you, speakers, for donating your time to contribute to this. And give yourselves all a round of applause for attending. It's a real thing. You can applaud yourselves. You donating your time to come here and be a part of the discussion in the community to further these ideas, it's an important part of what keeps this conference alive. But let's keep the applause going. I want to shout out to all the organizing committee members who put this on. Most of them are here, and you've seen scurrying around the room. But yes, as I mentioned at the beginning, this is all volunteer time for all of us. We do it because we feel this is a really important conference to have, and we really enjoy seeing the talks and ideas that come out of it. And once again, let's thank our AV team who did a great job all the 2 days. Thank you all, and again for Laura and Terry, our real-time captioning, who furiously kept up with the entire conference all 2 days. It's really amazing every time I see it. So give them a round of applause. And there's probably more people to thank, but you're probably all clapped out. And you're probably interested in knowing about 2017 as well. Anyone interested? Anyone willing to take a guess where GTAC 2017 might be next year? Mars, good guess. That'll count on SpaceX, how fast they can develop, if we can have it on Mars. All right, enough of the suspense. London, back to London. 2017. So yes, we will come full circle, and we hope to see most of you there again next year. We will be announcing a call for speaker proposals and invitations to attend on our testing blog. So be sure to subscribe and follow the testing blog, and all announcements will be made there. But once again, thanks everyone for coming. Don't forget any of your purses, luggage, anything as you leave. And hope you had a great time. Have a great trip back from wherever you are.